Good morning, Girijan sir.
Good morning, good morning, good morning, everyone.
Still time is there. We will wait.
Yeah.
So, can you hear me properly, sir? My voice
Yeah, you are perfectly audible. Perfect. Good morning, Amol.
Good morning, sir.
Good morning, Amol.
Can you hear my voice?
Yeah.
Okay.
Mata has joined?
He will join after 5 to 10 minutes.
Okay, fine. No problem.
Yes, sir.
Amol, your presentation is ready, no?
Yes.
Yeah. Amol, I will be completing my session, say, latest by around 12:15 or 12:20. Okay.
Okay, sir.
And after that, you can start with your software discussion.
Yes, sir.
And by around 12:40, 12:45, 12:50, you can take about half an hour, 30-35 minutes, not a problem. And
Yes,
then we'll keep around another 10-15 minutes for any question answer from the students and participants.
Yes, sir.
So let us by around say 1:15, maybe 5-10 minutes here and there is okay. By 1:15, today because I am starting a little late because there is from 10 to 10:40 there is an inauguration ceremony.
Okay, sir.
So I will not be able to start exactly at 10 o'clock. I will be able to start only around 10:45 because of the inauguration.
No issue, sir.
So that is why I may go up to around 12:15, 12:20. After that, I will call you. Then after that, you can directly take over and start with your presentation.
Okay, sir.
Madam Nagarazu, am I audible? Madam, Selection Madam. Selection Madam. Okay. Okay, thank you, Suchi Trivedi. Thank you very much.
Hello, Venkana sir.
Madam, just I want to check the voice. Is it okay now? Audible? No problem.
Okay, sir.
Okay. Thank you, madam. Thank you.
My voice is audible?
Your voice is excellent, madam. No problem.
Okay, sir.
Okay.
Sir, you got link, no? Even now also, because
Just now.
Professor asked to.
Just now you sent it again.
Yeah, Professor asked me to send one more time. That's why I sent to everyone.
Got received, madam. Everyone received.
Okay, sir. We'll start
Okay,
to
good.
sharp 10 o'clock once sir comes.
Okay, good morning, Girijan sir.
Good morning,
Namaste.
sir. Good morning. Good morning.
Namaste.
Namaste, sir. Good morning.
Sir Girjan sir, Professor Venkatnath is our HOD.
I know.
Chemistry
Thank you, sir.
department.
I am so happy to meet you virtually.
Thank you, sir. Thank you. Okay, Silashu Madam Garu made it possible. Okay.
So sir has joined, Professor sir has joined it seems.
Hello, hi, morning everyone.
Namaste, sir.
Namaste. How are things?
Good morning, sir.
Good morning, Sri Lakshmi ji. How are you?
Thank you, sir. I am fine.
Sri Lakshmi ji, before we start, I think one request to you.
Yes, sir.
I actually have another meeting at going on at 10 o'clock, same time.
Okay.
So I'll be here for about till my part is over.
Okay.
And then I'll move out into the other meeting.
Sure, sir. Definitely. That's not a problem. Thank you.
Good morning, sir.
Morning, Gajan ji. How are you? Thank you.
I am good, sir. I am good. Thank you so much.
Yeah. Thanks for working with our team.
It's my pleasure, sir.
Good morning.
Good morning, sir.
Good morning. Yeah, Girijan Saab, I am able to see you.
Yeah, good morning, sir. Good morning.
Good morning. Good morning. You are from Bangalore?
I am from Kerala, sir. I am from Kochi.
Kochi. Oh.
But I am settled in Mumbai.
Settled in Mumbai?
Yeah, yeah.
You are still working?
Still, I am working as a consultant after retirement.
How come you moved to Mumbai?
I mean, last more than 40 years, I'm in Mumbai, sir.
No, I did the reverse. Actually, I was in Mumbai for 37 years.
Okay, okay.
I came to Hyderabad 4 years back.
Okay, okay.
Nice.
Because immediately after my education, I came to Mumbai.
Oh.
And then got settled here.
Okay.
Now I consider I'm a local Mumbai car.
Mumbai car. I also feel comfortable being a Mumbai car.
Where were you staying, sir, Mumbai?
I was in Anushakti Nagar. I was in
Anushakti Nagar. Okay, okay.
Anushakti Nagar.
Good morning, Ramaraj sir.
Good morning, Amma. Sri Lakshmi. Yeah.
Yeah, good morning, Professor Atul, sir. You are in mute, sir.
Okay, good morning to all. Good morning, Rao sir.
Good morning. Good morning.
Good morning, sir.
Good morning. Good morning, sir.
Good morning, sir.
Good morning.
Thank you, sir. Welcome all. Welcome you all aboard for this e-com workshop. So we just get started, sir. Thank you for coming.
How many are registered?
Sir, as per data, we have around more than 900 registered students.
Good number.
Yes, sir.
Congratulations.
So, yes, thank you, sir. People are joining slowly. I mean, they're coming in little batches. We have sent a reminder again at 9:55.
Oh.
So hope soon probably more students will join.
Okay. Good. Anybody from other parts of the country other than Karnataka and Telugu speaking states?
Yes, sir. Yes, sir. I think around 100 participants are from outside Karnataka, Andhra Pradesh, and at least 10-12 students have been told from like other Middle East countries.
Oh, yeah.
Yes.
Time suits for them also.
Yes, sir. Time suits for them. That's correct.
It's a good number, sir.
Yes,
Yeah,
it
it's
is
a good number.
The topic is very interesting, very contemporary topic, you know.
No, I was wondering, but this is a very broad area you have chosen.
Yes, sir.
In materials, I mean, so it is a very broad area. Materials means right from metallurgy to engineering to medical.
But sir, the background, the context would be the chemistry actually.
Yeah.
Chemical characterization. Chemical characterization.
Because in our this campus, the material science is basically done by both the physics and the chemistry faculty. So their research
Sir,
kind of overlap.
in fact, as a mechanical engineer, we also make use of material science. In fact, when I
Yeah,
was in
yeah.
IIT Bombay, in
Yes.
fact, we were very, very active in these domain areas.
Yeah.
Materials are the key, actually. Whatever you do or whatever application or any kind of application. So materials for fabrication, their properties and all that is around. So.
Mm.
So,
Still 3 more minutes, sir.
yes.
Girijanji, you are in Mumbai only now?
I'm in Mumbai, sir. I'm at home.
Which part of Mumbai you are staying?
I stayed Goregaon.
Oh, Koregaon, Western.
I am from Powai, sir.
Achha, you're from Powai. Oh, very good, sir.
Now, after retirement, I have settled in Kharghar.
Kharghar. Okay.
Kharghar, that is.
A new Bombay.
Navi
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 Mumbai.
Navi Mumbai. Yes.
Kharghar is a well-developed place, sir.
Still, I have a house there.
Yeah.
Difficult to detach from Mumbai.
I know. Once you're used to Mumbai life,
Yes.
I mean, it's the
more
fastest life you can think of. Fastest life.
But more discipline. That's why you don't feel any difficulty.
Yeah. But people are all busy always.
Yes, commitment.
We normally say Mumbai never sleeps.
Yeah. That feeling gives a good, thrill.
Yeah.
Yes, we are in such a city where nobody sleeps.
Even if you come out at the middle of the night, you will find a chai wala on the street.
Yes.
Chai wala and vada pav.
Vada pav.
Yeah.
I want to introduce vada pav in our food science. At least some taste of Mumbai should be there.
Yeah. I feel it's the most popular food item in Mumbai.
Yes.
Street food item.
Yes, everywhere.
And so Bhelpuri as well, vada pav.
Yeah, Bhelpuri. Sir, even if a person has got only 10-15 rupees, he can fill his stomach in Mumbai.
Yes,
Not an issue.
Yes.
Not an issue. Not like other parts of the country.
Correct. Everybody can live in Mumbai.
Everybody can live in Mumbai. Survive.
And Shettis, they are basically from Karnataka. Many Shettis have become filthy rich.
Yeah, filthy rich because they were all running the restaurants. No.
Yeah, one Shetty bought the house of Vijay Malaya in Goa.
Okay. Yeah. All Udupi restaurants were all owned by Shettis. But now I think there is a decline because of so many fast food joints have come up in Mumbai. And because of that, there is a slight, there's a slight reduction in the number of Udupi restaurants.
And I'm told they only have initiated this also.
Yeah.
Yeah, good morning, Rao sir.
Hi, morning, Ramalagar. Morning, everyone.
Yeah.
Good morning, sir.
Good morning, sir.
Good morning, Atul. Atul, should we get going? It's 10 o'clock now.
Sorry. Sri Lakshmi?
Yes, sir. Shall I start?
All set to go?
Yeah, I think. Yes, ma'am, please.
Yeah. People are still coming in. And since Sir has to go, I think better.
Better to start in time.
Yes. Please.
Well, all the dignitaries, guest speakers, faculty members, and my dear participants, a pleasant morning to all. I, Dr. Srilakshmi, convener of the workshop, extending my warm welcome to all on behalf of Geetham Deemed to be University, Bangalore, and Department of Chemistry in association with Toshwin Analytical Private Limited to the 4-day National E-Workshop on Modern Analytical Techniques for Material Characterization. I am extremely happy to inform you that a total of 1,061 participants have registered for this workshop. This shows the importance of the topic for the current research problems. I also would like to especially welcome the participants from various parts of the world, namely South Africa, Yemen, Spain, etc. Thank you for taking time out and being here today. Lamp is a symbol of light or knowledge. It gets destroyed in ignorance and darkness. That's why diyas are lit and offered to the gods. Now I request everyone to pay attention to auspicious lamp lightning as a tribute to Mother Saraswati, the goddess of knowledge. Let's have a digital lamp lightning, please. Over to Dr. Nagaraj.
कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः.
Thank you, Dr. Nagaraju. It is mark of our undying tradition to invoke the Almighty at the beginning of an important event. Now, I would like to request Ms. Vakdevi to pray for us.
महागणपतिं मनसा स्मरामि महागणपतिं मनसा स्मरामि वसिष्ठवामदेवादिवन्दितं महागणपतिं मनसा स्मरामि महादेवस्तुत गुरु गुहानुतं महादेवस्तुत गुरु गुहानुतं मारकोटि प्रकाशं शान्तं महाकाव्यनाटकादिप्रियम् महाकाव्यनाटकादिप्रियं मूषिकवाहनमोदकाप्रियं महाकाव्यनाटकादिप्रियं मूषिकवाहनमोदकाप्रियं महागणपतिं मनसा स्मरामि महागणपतिं मनसा स्मरामि वसिष्ठवामदेवादिवन्दित महागणपतिं मनसा स्मरामि.
Thank you, Ms. Vakdevi. We all feel blessed indeed. It is a great privilege to pay tribute to our beloved founder and former president of Geetham, Dr. MBBS Murthy Garu, a proven visionary and philanthropist. Let me play a tribute video of Murthy Garu. Over to Dr. Nagaraj. Thank you, Dr. Nagaraju. The Department of Chemistry, Geetham, Bangalore, was established in 2012. All the faculty have a wealth of research experience with considerable abroad, doctoral as well as postdoctoral research and industrial experience, and are pursuing many innovative research projects with funding from agencies like UGC and DST. Major research areas of the department include catalysis, sodium-ion batteries, natural product synthesis, carbohydrate research, environmental science, and toxicology. Currently, the chemistry department have several research scholars pursuing PhD program in various basic and applied research projects. The department offers undergraduate courses in BSc MPC as well as BS Honors Chemistry and postgraduate courses in chemistry with specializations in organic chemistry and analytical chemistry. During the ongoing pandemic, the department has organized successfully a national and an international conference, a faculty development program, and various COVID-19 related online events. And for the first time, the department is organizing this workshop on modern analytical techniques for material characterization. And I am very happy in being the convener of the program. Well, in this juncture, I would like to recall a quote by Frederick Sayce. Individual curiosity, often working practical ends in mind, has always been a driving force for innovation. So you might wonder why we are conducting this workshop. Materials are probably more significant in our everyday life than what we realize. From transportation to housing to clothing and to food production, every segment of our daily lives is influenced by materials. Materials have contributed to the advancement of a number of technologies, including medicine, health, information and communication, national security, space, environment, and so on. As the contribution of material science and engineering to other disciplines increases, it will become necessary for scientists of all backgrounds to better understand the properties of these materials. This can be achieved through material characterization by using advanced techniques or by using techniques with advanced knowledge. And characterization is an important field in the area of material science. It refers to determining the physical, chemical, as well as structural and morphological properties of a material for a better understanding. This high level of knowledge can then be engineered to optimize the synthesis of materials to suit to their performance. The analytical methods routinely used in industry, research laboratories, and academics include different types of chromatography and spectroscopy techniques, along with many other measurement systems. Learning these techniques in a systematic manner is not just a requirement, but absolutely essential to fully exploit the potential of these methods. This is because the understanding of the subject mainly comes from the strong basis of the experiments and techniques on which the theories are built. The first Nobel Prize in chemistry was awarded to Jacobus Hendrikus von Hoff in 1901. Since then, this prize has been awarded 112 more times, and analytical chemistry related achievements have been given the prize roughly 10 times, which highlights the importance of the subject. To name a few, analytical chemists Archer John Porter Martin and Richard Lawrence Millington Sims were awarded the Nobel Prize in Chemistry in the year 1952 for their major contributions in the field of chromatography. Likewise, Richard Robert Ernest, a Swiss scientist, was awarded the 1991 Nobel Prize in Chemistry for his contribution to the development of the method of high-resolution nuclear magnetic resonance spectroscopy. In this proposed 4-day training program, 4 important analytical techniques such as UV visible spectroscopy, FTR spectroscopy, thermoanalytical techniques, and gas chromatography will be discussed in detail, emphasizing both the theoretical as well as practical aspects of the techniques. I hope everyone will utilize this opportunity to learn and experience and apply the knowledge gained in this workshop in their research as well as in teaching. With this, I welcome once again all the participants to the 4-day workshop. Finally, I wish you all a happy and productive workshop. Stay safe. And I feel very proud and honored to be with Geetam. And I would like to convey my sincere gratitude and thanks to our Honorable President of Geetam, Sri Bharat Garu, and Professor Ramakrishna Rao Garu, Chancellor Geetam, Professor Sivaramakrishna Garu, Vice Chancellor Geetam, Professor D. Gunashekaran Garu, Registrar Geetam, and Professor A. Subramanian Garu, Dean Sciences Geetam, and Professor D. S. Rao Garu, Pro Vice Chancellor Geetam Bengaluru, Professor A. Ramarao Garu, Principal of Science Geetam Hyderabad, Professor Atul Kumar Garu, Principal of Science Geetam Bengaluru, Professor Dinesh Seth Garu, Director School of Technology Geetam Bengaluru, and Professor Venkatnath Garu, HOD, Chemistry Department Geetam Bengaluru. And to all my colleagues for providing me this opportunity and support to organize this workshop, which will be extremely useful and enlightening to researchers. Now, we are eagerly looking forward to hearing the dignitaries' address. Now, I request Honorable Pro Vice Chancellor Professor D.S. Rao Garu to preside over the workshop.
Thank you, Sri Lakshmi.
Thank you, sir.
I think good morning, everyone. I think I must congratulate the chemistry department of Geetam University, Bangalore for organizing this workshop, and I also should thank Toshwin Analytical Private Limited and Mr. Girijan, who is present here today, for collaborating with Geetam University for conducting this workshop. I think the importance of the basic sciences and the physical sciences, I think, need not be more emphasized. I think Sri Lakshmi has given a brief understanding and overview of the importance of the chemical sciences as well as the physical sciences. I think most of the fundamental problems that are facing the world today, I think, for example, the energy storage. I think the biggest problem that the world facing today is to how do you get out of the fossil fuels, and if EVs have to be used on a regular basis and it has to come to the mainstream, the current hurdle is the storage capacity. I think that will fall in the very core domain of the chemistry and the nanotechnology areas. And what is it that our scientists from India, I think there are a large number of researchers working on this particular domain of how do we increase the capacity of the storage. Either the power is coming from either from solar or wind, wherever it is. But if transportation has to be possible using EVs, so I would like to throw a challenge at my faculty members and all the scientists participating in this session. And I would guess, the large number of them from India. I know there are a large number of you are already working on a particular domain. But this is a core problem that the world is facing today. And if we had to be concerned about the environment, I think if we can increase the storage capacity to a commercially viable level, I think that will be a great thing to do. Another area where the world is working on today is again the conversion from solar energy. I think the efficiency currently is not more than I think 10 to 11%. Is there a way that our scientists can work on the conversion of the solar energy from the current efficiency levels of about 11-12%, even a few percentage points more would increase the available energy to the world substantially. I think these are two core areas. I know there are many other areas, but these are the ones that could have a massive impact on the humankind and on the environment today. And I think I should congratulate, but all of that science starts with the material science. How the material science is being configured to be able to either store energy or convert energy from solar energy to electricity. Unless we understand deep into the material sciences, these developments would not be possible. I'm sure this workshop would go in a long way to equip all the faculty members and research and upgrade their skills in terms of using the advanced techniques to understand the materials a little more deeply, and would also help you in your own area of research, irrespective of which part of the chemistry or the physical sciences you are working on. Once again, my congratulations to the entire team of Geetham University and Toshman Analyticals, Mr. Girijan, for sparing your time over the next 3-4 days in helping our faculty members and the researchers understand the new tools and the techniques. Thank you very much, and I wish you all the very best for this 4-day workshop. Thank you.
Thank you, sir, for your challenging remarks. And definitely we should look into this one, and we will take it as a project. Now I request Professor Ramarao Garu, Principal Science Geetham, Hyderabad campus, to address the participants.
Thank you very much. At the outset, I thank the organizers for giving me this opportunity to speak on modern techniques. Actually, this has been a challenge in numerous fields of experimental and theoretical studies in terms of applications and measuring methodologies in different specificity and the requirements of various users, end users, and in analytical instrumentation brought many daunting challenges for the development and the community to develop very complementary techniques. Many instruments are there, but for always we need a complementary technique, because one instrument cannot give all the information that you desire, and many hyperfine instruments, they are coming with complementary measurements like TG, DTA, DSC, and all that. Two or three kinds of information can be obtained from one setup of instrument. But what basically this experience, I feel sorry to say that our India, we are not progressing in, we are using the instrument, we have got expertise, but we are not training the next generation how to develop the instruments. Okay. And even simple experiments we can design in the laboratory to give a freedom to our students to think of developing something. A simple like thermocouple. It's a very, very simple thing. A thermocouple for heat measurement that we buy from market, but we never make at office. It is a simple brazing is required. That's all. Two metals can be brazed and different metals can be brazed and make a thermocouple. Student will be happy because he has got one technique. So this kind of experiments we should encourage in the curriculum, so that students will think of developing something, not just following what is already designed and what is kept in the syllabus. Instead of that, something more. And actually, when I joined here, and there was one experiment, heat capacity measurements. And that experiment was not being conducted because there was no instrument, there is no calorimeter. So I took a while, and then when I still remember during some time in 10th class syllabus, if you take, textbook if you take, there they have given this heat capacity measurement by taking only a beaker. And by beaker, you can do heat capacity measurement, mixing two solutions of different temperatures and see the weight loss, how much weight loss is gone, and weight loss, or no, sorry, not weight loss, heat loss, and how much heat is absorbed by your container. That is the heat capacity of the container. See, when you give the instrument of heat capacity calorimeter and ask the instrument to do an experiment, it is like a idiot box. He doesn't know what is happening inside. He may get a value, he may report a value, but he doesn't understand what is heat capacity. But if you do it with a simple kind of experiments like this, with a beaker, and finally one of our students has developed with a copper vessel he has brought, and gave an insulation around, and he has found out the heat capacity of the copper calorimeter. So we should drive the students for this kind of innovations. This is the age where they have to think of development. It's not that somebody will develop and we will use it and we will get the data, we will publish it, we will get the paper. That's not the one. It's not working properly. And so far, and when USA banned supplying of many, even computer they have banned for our organization, like Department of Atomic Energy. So that gave a kind of adversity for us, that we should develop our own. Even a computer chip, it was not available during that time. And we made many instruments during that time. Even a simple furnace we can make in our laboratory. A simple furnace. It may not be that accurate, but you can make a good zone, good heat zone, and with an instrument. But that is how we should learn. Nothing goes waste in that, except one aluminum tube and a Kenthal wire. You can ask the students to design. It's not necessarily only an engineering job. It is a chemist. A chemist ultimately is using the furnace and a thermocouple, heat measurement. We can do that. So this is what many techniques are happening, and when new instruments are coming in every field: medical, environmental, pharmaceutical, industrial, and food control. Food control also, many instruments are coming with a lot of food adulteration happening, and everybody is keen to have a good, nutritious food and quality food and safe food. So many instruments are happening to characterize the food also, and this is one should enjoy the thrill of using a particular technique to get the instrument, to get the materials. A lot of materials are being developed, particularly in space, atomic energy, alloys, many alloys. Okay, and for characterization, you need a lot of new instruments which can give information in a very quick manner without taking much time, and valuable information, and also a kind of challenge to look further what in improvisation in terms of miniaturization becoming a very small one. Recently BRC has developed one ECG machine, like your mobile. You can use your mobile and get the ECG data of any particular a patient. So this kind of innovations will happen only when you force them, when it becomes compulsory. Otherwise, our Indian mind, we don't do. As long as it is available, we never bother. That's why many things are not happening, many things are not available in the market. But only recent awareness came because of COVID that we are started looking for whose product it is, whether it is a Chinese product or somebody's product. But many people are not trying to improve because of one reason: fear of failure. And we have never trained our students what is the thing that you can learn out of failure. Always scared, students are scared of failures because we always discourage them to fail. And failures teaches many things. They teach many things, so that next time, how many times they will fail? At least once they should fail. Then only they will understand what is called success. So for the fear of failure, nobody makes an attempt even to develop anything, to work on any new topic. So this is what I want to request all my faculty, young faculty, to look for something which you can train the students, you can motivate the students to develop few techniques which can be made in the laboratory. You see the thrill, you see the enjoyment that student will have once he does something in the lab itself. Thank you. I don't want to take more time on this. Thank you very much. I wish the program all success, and it's nice to meet some of our new people, Girijan and other from Mumbai. And Atulji, thank you very much for giving me this opportunity. Sri Lakshmi ji.
Thank you,
Please,
sir. Thank
please
you
go
very
ahead.
much for your wonderful remarks.
Please go ahead.
Now I request Professor Atul Kumar Garu, Principal of Science, Geetham, Bangalore, to address the gathering.
Thank you, Dr. Sri Lakshmi, for inviting me to speak to our participants what they should do in this conference. I mean, this is indeed a pleasure to be here to speak to all the participants, and I must thank you and your team, Dr. Vikram, Dr. Nagaraju, and the department, Professor Venkatanath, for pulling this up and then just organizing this great conference, which is through the e-workshop, through internet. And I thank our senior Professor Rao for giving such a wonderful context to this conference, and telling us how should we encourage our students to do better things which we could not do. Anyway, so there's another thing. I just want to talk to the participants that this is a conference or e-workshop on the analytical techniques in material science. As we know, the material science is a vast field. It is span all the discipline of study, be it physics or chemistry or the space or whatever. And materials, I mean, as a man progresses, the invent or desire for the new materials are enormous, right? As correctly said by our honorable Pro Vice Chancellor, is that for energy storage and for other applications, you need to resort for new kind of materials which can hold the energy for longer time for different applications. Similarly, my field is optical communication, so I can say that the future belongs to optical computers, where the new materials are desired, where all the optical processing can be done in optical domain without resorting to the going back to the electrical domain. So the future would be the optical computers, where all the processing, all the bits and digits should be done in the optical domain. So the future is very interesting as far as the material science is concerned. Lot many things have been done in past, and the young researcher or the undergraduate or postgraduate students have a lot more going for them. This is a platform where you can learn the basic technique of material characterization. In this conference, the 4 techniques like ultraviolet, thermography, chromatography, and FTR technique will be taught to you. So my appeal to all the participants is this, that kindly sit through the lecture for 2 hours, take appropriate break, take notes, listen to the lecture carefully, because Professor R. Grijan is a top-notch person in instrumentation, and probably he's going to tell you the many tricks, many things, the whole process, the physics behind the instrumentation, and how to use the equipment. And of course, he's going to represent his company, which is Shimazdu and Toshvin. So kindly, this is the beginning for you people to learn through online the techniques of characterization, which will go a long way in building your maybe good research career in the time to come. With these words, I stop here, and I'll wish you luck, and I'll say please take notes while you go through this conference, right? And all the best to all the participants. Thank you so much.
Thank you, sir, for your encouraging words. Now I request Professor Dinesh Seth Garu, Director, School of Technology, to say a few words to the participants.
Good morning, one and all. Thanks for having me here. I welcome Dr. Girjan, Professor Rao, Dr. Atul Kumar, and other dignitaries. On behalf of Geetam, Bangalore campus, I'm thankful to Toshnibal and Chemistry Department for organizing such a wonderful event, which is very, very timely. In fact, I will say that we are making use of the festive breaking time between Dashera and Diwali, and we are making use it for our learning purpose. Material characterization is an important field. I will say it is the root for many disciplines. Professor Rao quoted the example of solar cell and battery. Similarly, if we want to develop a new injection for COVID-19, or if we want to develop newer fabrics for our soldiers who are operating at a height of 8,000 meters at a temperature condition of -40 to -40 to -60 degrees centigrade, we need to develop newer clothing material. In fact, our borders are very, very hot, and we need more types of missiles, better types of missiles. How these materials and missiles can be developed, provided we understand the ABCD of material characterization, and we know after understanding the characterization how these devices, how these materials can be utilized. So the characterization of material is a very, very important basic fundamental step before we talk about the ABCD of utilizing material for any purpose. And this characterization can be of many types. It can be mechanical characterization, thermal characterization, chemical characterization, optical characterization, electrical characterization, or maybe a situation specific characterization, which makes us to understand the materials, what we are considering, whether they are fit, whether they can perform necessary functions, or will create certain challenges for its usage. So measuring and understanding material behavior, measuring and understanding materials property will definitely enrich the domain of experimentation and will facilitate the application part. I would not like to act as a barrier between Mr. Girijan and the participants, you know, because you all are here to listen him, not to me. So I hope that this workshop organized by our Department of Chemistry and supported by Mr. Stoshniwal will be very, very useful and will enrich you uh, about the newer changes which are happening in this domain area, and you will come to know about state of art of these 4 domains, whether it is spectroscopies, whether it is FTIR, whether it is chromatography or the thermal analysis. With these few words, I wish you all the success. This 4-day workshop on material characterization. The only appeal which I, as a director, I want to make to all of you is that please make use of this golden opportunity for learning. In fact, and workshop means it should be 2-way traffic, not just 1-way traffic. So I expect that once the speaker has finished his session, please raise intelligent questions. With this, once again, I extend all my wishes for this event. Thank you.
Thank you, sir. That is very encouraging. Now, I request Professor Venkatnath Garu, HOD, Chemistry Department, Keetham, Bangalore, to address the participants.
Okay, good morning to one and all. It gives me pleasure to place on records about the thanks of Department of Chemistry to the Keetham management and administrators for encouraging us to conduct a good number of activities even during the pandemic period. During the last 6 months, the faculty members of Chemistry Department were able to organize 2 webinars, 1 week faculty development program, national level student competition on creative awareness on COVID-19 and international symposium. This is one more program that is we are going to conduct under the leadership of Dr. C. Lakshmi. In addition, one more international conference is scheduled in the first week of December 2020. On behalf of Chemistry Department, I welcome all the delegates and the resource person, Mr. Girijan. Request all the delegates for active participation in the workshop with fruitful interaction with the resource person. Thank you, Ananda.
Thank you, sir. Now, I take this opportunity to introduce our guest speaker and resource person of our workshop, Mr. R. Girijan. Mr. R. Girijan is a product consultant in the field of analytical instrumentation with around 42 years of experience in the analytical field. He is a postgraduate in analytical chemistry from University of Kerala. He is a fellow of the Institution of Chemists, India, member of the American Chemical Society, and life member of Indian Society of Industrial Chemistry. He worked in pharmaceutical as well as paints and polymer fields and has approval from FDA Maharashtra in the field of chemical and instrumentation analysis. He has extensive experience in chromatographic and spectroscopic analysis. He does guest lecturing at various institutions of national repute, corporates, as well as universities and colleges. He had undergone advanced training in the field of chromatography and spectroscopy at Thermo Fisher Scientific, UK and Italy, and also at Shimadzu Corporation, Japan, China, and Singapore. Currently, he is working with Toshwin Analytical Private Limited, Mumbai, as a product consultant. I am thankful to Mr. R. Girijan for accepting my invitation for being the resource person to this workshop. Thank you, sir. Today's session is on UV visible spectroscopy, which will cover basic theory of UV visible spectroscopy, instrumentation, including demo, and applications of the technique with suitable examples will be explained by our resource person. Now, I hand over today's session to Mr. Girijan and his team. Girijan sir, screen is yours.
Thank you, sir. Thank you, Dr. Lakshmi. Thank you very much. A very good morning to all the participants. First of all, I'd like to thank the management of Keetham for giving me a chance to be a part of this wonderful program. I really feel honored. I would like to place on record my deep appreciation for the initiative taken by the management of Keetham and especially Dr. Sri Lakshmi in organizing such a wonderful webinar series, especially for the benefit of students. We are all getting used to a new normal because of the current pandemic situation. And we all know online teaching, online learning have all become the order of the day. And I'm sure these type of programs will enable the students to refresh what they already know and what they have already learned. So during this current 4 days, during these 4 days of program, I am going to briefly discuss about four important analytical techniques, which are very, very widely used in industry, research, as well as in academia. I am working with Toshwin Analytical Private Limited, Mumbai, in the capacity of a consultant after my retirement from the company. Toshwin is in association with Shimatsu Corporation of Japan for the last 50 years. We started our association with Shimatsu in the year 1970. So it's a long association. And Shimatsu is one of the world leaders in the field of analytical instrumentation. And Toshwin is a customer-centric company. We have a large customer base of approximately 8,500 and with around 15,000 instruments working in various fields across India. And this is, I just wanted to tell about my company very briefly. Considering the time limit, with these few words, I am going to start with the topic of today's discussion. So I'll start with UV visible spectroscopy. That's the first topic. What we are going to discuss about a very brief discussion about the basics, some of the important applications, and a bit about the instrumentation of UV visible spectroscopy. Okay, so I'll start sharing my screen.
Yes, sir, please.
The screen is visible?
Yeah.
Okay. So once again, good morning, all the students. What we are going to discuss, what I am going to discuss, starting today or the next 4 days, 4 different techniques. My aim is only to briefly discuss about the basics and the fundamentals of the technique. I am not here to teach you something advanced, something which is totally new. What we are going to do is discuss about the basics of the techniques, and everyone will agree with me, I'm sure. A very good understanding about the basics of the technology of the technique is very, very essential in building up the knowledge. You know, we can construct a very tall building, maybe 30, 40, 50 floors, provided the basement is very, very strong. Otherwise, the building will collapse like a pack of cards. So once the base is strong, you can always build upon that. So I have a very limited time, hardly 2 hours to talk to you. And during this time, I am going to discuss about the basics, which you have already learned. I know all these are there in your curriculum. You must have already learned about all this. And we are trying to refresh. Many times, I know, because I am an industry person, I spent almost more than 22 years in industry, both pharmaceutical as well as polymer. I know the pressure of working. I know the pressure of working in a corporate world. And as students, you have certain responsibilities. Today, you are in the university. Tomorrow, you are going to be out of the university. Many of you must be going for higher studies. Many of you must be getting into corporate world. And the moment you get into the corporate world, I can tell you very frankly, my dear students, you are going to be your own masters. See, when you are in the university, when you are in the college, there are people to take care of you. Your teachers, your professors, they are there to take care of you. But the moment you get into a corporate world, you are your own master. There is no spoon feeding at all. Nobody has time. Everyone is loaded with his or her own work. So nobody has time to sit with you, to teach you, to guide you. Okay, there are people to guide you. I don't say no. But everyone is having their own workload, because end of the day, you are responsible for your quantum of work that is assigned to you. So if you are very, very thorough with the basics, and you are getting an opportunity in your college, you are getting an opportunity in university to learn all these techniques. And the moment you get into an outside world, a corporate world, you are confident enough to work by yourself. And that's all what we are going to discuss. Very, very simple things. I'm not going to talk to you regarding any of the advanced techniques. In the course of the discussion, we will talk about some advanced accessories which can be used for characterizing certain materials. But what is more important is understanding the basics. So we are starting with the UV visible spectroscopy. I specifically selected UV visible spectroscopy because it is one of the simplest technique that is widely employed, widely used, both in industry as well as in academia. So when we talk about any of these techniques, any separation techniques or spectroscopy techniques, they're all collectively called analytical techniques. And when I say analytical techniques, they're all coming under analytical chemistry. I myself is an analytical chemist by profession. So analytical chemistry deals with separation, identification, and also quantification of different types of samples and materials. Analytical chemistry utilizes classical wet chemistry methods because we are all working in whether it is an academia or industry. Along with instrumental methods, we also have classical wet chemistry methods. Every industry has got a wet chemical lab, and a lot of experiments are carried out there. So we cannot underestimate the importance of classical wet chemistry methods. So analytical chemistry utilizes classical wet chemistry methods as well as modern instrumental methods. Both are important. And instrumental methods will include chromatography separations, spectroscopy identifications, and there are a lot of other material characterization techniques also. Under identification techniques, we have different category. So many members are in this family. And to name a very few which are very, very commonly used, starting with the simplest one, UV visible spectrophotometry, infrared spectrophotometry, atomic absorption spectrophotometry, inductively coupled plasma atomic emission spectrophotometry. It can also be connected to mass spectrometer, then it becomes ICP-MS, fluorescence spectrophotometry. So there are so many members coming in this, and each one has got a certain role to play. And please understand, students, when you are taking a certain analytical technique, it is not sufficient to characterize the material totally, because every instrument is designed to give you a certain piece of information. A totally unknown compound cannot be characterized by a single technique. You need to use different techniques. You need to collect data from different experiments. You need to pull out all this data, and then only you can come to a definite conclusion as to what is the identity of the material. So every instrument is designed. For example, UV is designed for a certain type of work. IR is designed for a certain type of information. And there are so many techniques. Each one is designed for a certain type of information. And when you talk about specifically about spectroscopy techniques, it can be broadly divided into molecular spectroscopy as well as atomic spectroscopy. And our topic, today's topic will be coming under molecular spectroscopy, UV visible, FTIR, Raman, NMR, they are all molecular spectroscopy. When we talk about atomic spectroscopy, we have again atomic absorption, we have inductively coupled plasma, all those are coming under atomic spectroscopy. Everyone knows about electromagnetic spectrum. I need not spend too much of time on that. Electromagnetic spectrum is nothing but a certain systematic arrangement of different types of radiations available today. Now, what we look at the sunlight, white light, it's also a type of radiation having a certain wavelength range, certain energy content. Similarly, we have different types of radiations available. I mean, UV is one type, visible is another type, infrared is a different radiation. So like that, so many radiations are available, and each radiation is characterized by two properties. One is the energy content and one is the wavelength. And this will be different from radiation to radiation. And we try to arrange this in a very orderly manner, very systematic manner. We get what is called an electromagnetic spectrum. And what you see here is a part of electromagnetic spectrum. And if you look at the slide, on the extreme left-hand side, you have all radiations having extremely high energy content. And every student knows the relation between energy and wavelength. It has got an inverse relation. That means when the energy is more, your wavelength is less. And the other way around, when your energy is going to be less, your wavelength is going to be more. So on the extreme left-hand side, we are keeping all radiations having a very high energy content like gamma rays, X-rays, all those. And by virtue of their high energy content, the wavelength range is very, very small. They're very short wavelength radiation. And when you go to the other extreme, the right-hand side, you have very, very long wavelength radiations like radio waves, microwaves, all are coming on the right-hand side. And their energy content is also very less. Now, UV, visible, IR, they are all part of this family. And you can see that they are all coming almost at the middle of the spectrum approximately. And each type of energy has got a certain wavelength range also. For example, I have highlighted visible light. And everyone knows visible light is a combination of 7 different wavelengths, 7 different components, what we normally call as VIBGYOR: violet, indigo, blue, green, yellow, orange, red. And it has got a wavelength range starting from 400 nanometer and extending up to 700 or approximately 800 nanometer. That's the total wavelength range of visible light. So similarly, what we are going to see is the UV also has got a wavelength range. IR has got a different wavelength range. That is what we are going to see. Now, the radiation, the light can get propagated through the medium in the form of a wave. And everyone knows what is a wave motion. If you look at the sea, how the water is coming, water is going up and coming down, and the pattern is getting repeated multiple times. That is, the water waves are moving forward. So it is going up and then coming down. Similarly, when the light is also getting propagated through a medium, it has got multiple maximum points and multiple minimum points. And these are very, very basic things, you know. The maximum points are called crest points, and the minimum points are called trough points. And the distance between two consecutive crest or trough points are called one wavelength. That's what normally we call it as 1 lambda. And that represents the wavelength. And this can be different from radiation to radiation. And the very simple equation, C is equal to nu lambda, where C is the speed of light, lambda is the wavelength, and nu is the frequency. So these are very, very basic things we have already studied. And when the light is propagating through a medium in the form of a transverse wave, it has got certain phenomena attached to that. Like it can undergo transmission, it can undergo absorption, it can undergo refraction, and also reflection from a surface. So these are all some of the properties associated with a light wave motion. And this is exactly what I have told you. Now, what happens when the light strikes a molecule? My simple question is, what we are going to study using a suitable spectroscopy technique? Now, we are going to study what type of changes are taking place. Or in other words, I can say, what is the type of interaction that is taking place between the sample and a certain form of radiation. That means when a certain form of radiation is coming and falling on a sample, that is our matter, there are going to be certain changes that are going to take place. And these changes are what we normally study by using a certain spectroscopy technique. And the incoming radiation can be either of a high energy nature or it can be of a low energy nature. For example, if you recollect the electromagnetic spectrum, what you have seen in the previous slide, if you compare the energy content of IR and UV and visible, you know UV is a high energy radiation which is coming to the left-hand side of visible. And visible light has got more energy because it is coming on the left-hand side of IR. So compared to UV and IR is considered as a low energy radiation and ultraviolet is considered as a high energy radiation. So the changes that are going to take place when these radiations are coming and falling on a sample, on a molecule, these changes are also going to be different. So when a low energy radiation is falling on a sample, two types of changes can be, you can see two different types of changes that are taking place. One is called a vibrational transition and one is called a rotational. A transition is the change of a rotational transition. And when a high energy radiation is coming and falling on the sample, it's a totally different transition that is going to take place, an electronic transition that is taking place. And we'll see what is the difference between these. And the vibrational transitions are normally studied by infrared. So when you are going to have a discussion tomorrow on infrared technique, we'll be discussing more about vibrational changes that are taking place in a sample molecule when it is subjected to IR radiation. In the case of UV, it is an electronic transition that is taking place because UV is a high energy radiation. Now, different types of changes that can take place when the sample is subjected to a certain type of radiation. For example, if you consider UV radiation, UV light is coming and falling on the molecule on the sample, electronic transitions are going to take place. Very, very high energy transition, electronic transitions are high energy transitions. And for an electronic transition to be to take place, the incoming radiation has to be a very powerful one. And that is what is taking place in electron transition. We'll see in the next slide, we'll see what is meant by electronic transition. But if a IR radiation is coming and falling on the sample, it is of low energy content. So naturally, electron transition will not take place. What is happening is a vibrational transition that is taking place inside the molecule. They are of lower energy. So between two energy levels, E0 and E1, E0 is the energy content of a sample at normal conditions. Normally, what we normally call as the ground state energy or the ground level energy. That's E0. And when I talk about E1, that is a elevated energy content, that is also an excited energy level. So between E0 and E1, there are different vibrational levels like V0, V1, V2 like that. So those type of changes can take place when the sample is subjected to IR radiation. Now there is one more, microwave radiation is coming and falling on the sample. It's a still of much lower content, energy content. And within two different vibrational levels, multiple rotational levels. So rotational transitions can take place. And rotational spectroscopy, we have microwave spectroscopy for studies rotational transitions that are taking place in a sample molecule. So now what we are going to see is electronic transition that is taking place in the sample when it is subjected to UV radiation. As I told you, any sample under normal conditions, it has got a certain energy content. We normally denote it as E0, ground state energy, ground level energy. Now, imagine this sample is subjected to UV radiation. UV radiation is coming and falling on the sample. Now, depending upon the type of sample, that's an important statement. Depending upon the type of sample, the sample will absorb a certain quantity, a certain quantum of energy from the incoming radiation. So what will happen? The energy content of the sample will increase because it has already got certain energy, which is E0. Now it has received additional energy from the incoming radiation. So the total energy content will increase and it will go from E0 to E1. E0 is the ground state and E1 is the excited state. Now, if you consider the difference between these two, E1 minus E0 is delta E, or you can call it as H nu, and that is the quantum of energy absorbed by the sample from the incoming radiation. Okay, now why we call it as electronic transition? Because we imagine the structure of an atom, because there is a central nucleus where you have all protons and neutrons, and around the nucleus there are a lot of electrons orbiting in different orbitals. So when it is subjected to IR radiation is coming and falling on the sample, depending upon the type of sample, one electron from the outermost orbit is getting elevated to a higher energy state. And because that is the reason why we call it as a electronic transition. And how many types of electronic transitions are possible? Different types. That is what we are going to see briefly. Absorbing species in UV visible. Every sample cannot absorb in UV. We'll discuss about that. I mean, that is why I told you, depending upon the type of sample. All samples cannot absorb. There are so many samples which cannot absorb in the working region of a UV spectrophotometer. And we'll see why it is so. See, now the sample is your M is your sample molecule, and H nu, that is the energy is coming and falling on the sample. What will happen? The sample is getting elevated to a higher energy state. It is going to an excited state. M is getting converted to M star. M is the ground state and M star is the excited state. But now this excited state has got a very, very short lifespan. It will come back to the original state, that is the ground state. So M star will come back to M. And with this process of coming back to the ground state, whatever energy it has absorbed will be given out in different forms. It can be given out in the form of heat. It can be given out in the form of fluorescence. It can be given out in the form of phosphorescence. So different forms it can come out and it will come back to the original form. So that is why in the fluorescence spectroscopy, what we are studying is what is the fluorescence that is coming from the excited molecule when it is coming back to the original state. Or there can be a different reaction, like M star is getting converted to a totally new entity. M star is getting converted to, and that is what when you talked about photochemical reactions. So these are the possibilities when the sample is getting subjected to IR, so UV radiation. Now in the atomic size, there are different molecular orbitals. Some of the orbitals are occupied and some of the orbitals are not occupied. And so it can be occupied levels or unoccupied levels. For example, sigma, pi, and then these are all occupied levels. And when we talk about pi star and sigma star, these are unoccupied levels. So there can be an elevation. There can be an elevation of an electron from a occupied level to an unoccupied level. Then the energy involved in this transition depends upon from what level to what level it is going. See, for example, some of the transitions involve very high energy content and some of the transitions may involve low energy content. For example, if you talk about a saturated hydrocarbon, normal paraffins or N-alkanes, normally the transition that is taking place is from sigma to sigma star. One electron can get elevated from sigma orbital to sigma star orbital. That's the highest energy involvement. Highest energy involvement or transition, sigma to sigma star. See, I will tell you a very simple thing to students, a practical point of view. When you are doing an experiment in UV, many times you have to prepare very dilute solutions. And because in UV, you have to have a very dilute solution for the measurement. So you are using different solvents. And many times you have to use a solvent which will not absorb in the working range of our equipment. Normally, most of the equipments available in the market today, which are available in the normal applications, the UV has got a UV visible spectrophotometer has got a working range from starting from 190 nanometer and going up to 1100 nanometer. So starting at 190 nanometer and going to 700 nanometer. So that's a normal scanned range. We call it as a scanned range of a UV visible spectrophotometer. So anything that is happening below 190 nanometer, we are not able to see because it is lying outside the range of our equipment. So when you are using a solvent, you have to use a solvent which do not have a considerable absorbance in the working range or wherever you want to make a measurement. For example, you are going to keep a certain wavelength for the measurement of your sample, what we normally call it as lambda max. We'll discuss about that later. And that solvent should not absorb. So normally, for example, if you consider a saturated hydrocarbon like alkane, normal hexane. Normal hexane is a very simple solvent, normal hexane. Normal hexane, we say it is UV transparent. That's a normally in industry also, people say normal hexane is UV transparent because it doesn't absorb, people believe it doesn't absorb UV radiation and hence it is called a UV transparent sample. And it can be used for making solutions for measurement between 190 to upwards. That's all. But in reality, normal hexane also can absorb. It is a N-alkane, it's a saturated hydrocarbon. And there is a transition that is taking from sigma to sigma star. But why we are not able to see this transition is the energy involvement is much on the higher side. And it is somewhere around 150 or 160 nanometer wavelength range. It is taking place much below 190 nanometer. That is why we are not able to see. If you keep a normal hexane in the UV spectrophotometer available in your lab and you start scanning from 190 nanometer upwards, you will not find any meaningful absorption for normal hexane because whatever is happening is below 190 nanometer. We are not able to see that because of the high energy content, sigma star content. So this is actually what is taking place in most of the saturated hydrocarbons. Then there can be a transition from sigma to pi star orbital. Many of the carbonyl compounds, the sigma to pi star transitions can happen. And we can many times, these are falling in the working range of our equipment, so we can see. When it is a transition from pi to pi star, most of the unsaturated compounds will have this type of transition and they're all falling in the working range of our equipment. So most of this can be studied very comfortably and conveniently. Similarly, samples containing oxygen, nitrogen, sulfur, or halogens normally have N to sigma star transitions. And there can be some carbonyl compounds where you can have even N to pi star transitions also, but these are all happening in the working range of our equipment so that we can actually see this. And this is what exactly I told you, sigma star alkanes. For example, it is happening around 170 nanometer. And if you talk about an unsaturated compound, they're all above 190 nanometer. We can see all those transitions. Similarly, some of the carbonyls also have got N pi star transition. This can happen somewhere around 300 nanometer region of the spectrum. So we can comfortably, we can study all those types. And the sigma electrons are involved in the single bond formation. Most compounds of atmosphere absorbs. So what is basically why we are not able to, in most of the instruments that are available in the market, they start with 190 nanometer. The reason is below 190 nanometer, even atmospheric oxygen also can absorb and interfere in the determination. That's the reason why normally people are giving an instrument starting from 190 nanometer upward. But we have certain equipments which can work below this. And below 190 nanometer, when you go, that region is known as vacuum UV region. It is not the normal UV region, it's called vacuum UV region. You need to evacuate the equipment. You have a nitrogen purging facility available, but we have certain equipments which can work in this region, but those equipments are quite costly also. But normal applications, whatever we are coming across, it can be a pharmaceutical application or normal chemical application, normal environmental application, anything. It can work from 190 to 1100 nanometer plus other. So that's the reason why they are giving this range. Similarly, pi bonds, pi electrons are involved in double bond formation. And I know this you have all studied in your elementary class also. And this is exactly what I've already told you. Different types of transitions, sigma star, N sigma star, N pi star, pi star, and those type of. And here I'm just giving an example few, and there are different columns. The first column is called, there is a chromophores are shown. What is a chromophore? You should understand. That is what I'm coming to the next slide. Especially for the students, I'm talking to the students. And the second column, some examples. And third column, what type of a solvent you can use. And the next column, what the lambda max. Lambda max, I am 100% sure everyone knows what is lambda max. Because a compound can absorb at various wavelengths when you are scanning it in the UV range. Okay, now, but at one particular wavelength, the absorption will be maximum. And that wavelength is known as lambda max. All your quantitative analysis, quantitative estimation should be carried out at lambda max value. Otherwise, your quantitative result may not be proper. So you should know what is the lambda max for your sample. If you get the value, you can directly use it. But if you don't know what is lambda max, you have to find out. You have to do a scanning of your sample from 360 nanometer to 190 nanometer. As I know, many of the students must have done experiments using UV. Your normal working region is from 190 nanometer to 360 nanometer. Your instrument has got a range from 190 to 1100 nanometer. I told you. From 190 to 360 is your UV region. 400 to 800 is your visible region, and beyond 800 you are slowly entering NIR region, near infrared region. Okay. Now your UV the actual UV range is from 360 to 190, and 400 to 800 is a visible region, and there is a region between 360 to 400. You will wonder what is that region. 360 nanometer to 400 nanometer is called the overlapping region. And what is meant by overlapping region? Because your instrument is UV visible spectrophotometer. You can use it for UV measurement. You can use it for visible measurement. The lamps are different. For UV measurement, you require a D2 lamp, deuterium lamp. And for a visible measurement, you require tungsten halogen lamp. The lamps are different. Ranges are different. And so when you are having a total scan right from 1100, and if you're coming to 190, there at one point of time, your tungsten halogen lamp has to changeover to D2 lamp. So there is a lamp changeover region. One lamp is getting off and another lamp is getting on automatically through the software. And that particular region is called overlapping region. That is the region between 360 nanometer, 400 nanometer. That's the overlapping region. Okay. Now you should know what is the lambda max. If you don't know what is the lambda max, you have to scan your sample from 360 to 190 and then find out what is the lambda max for your sample and use that lambda max value for your quantitative analysis. And UV is a 100% quantitative estimation technique. Why it is so, we are going to see. And what is that causing? When I said all samples cannot absorb UV, there are certain samples which cannot absorb UV in the working range of our equipment. So what is it that making the sample absorb UV? Some single bonds. May samples containing double bonds, most of samples containing a double bond can absorb UV energy. Conjugated double bonds, excellent UV absorbing material. And samples containing nitrogen, oxygen, sulfur, and halogens, they also can absorb UV. But there are certain samples which cannot absorb UV, and they are collectively called UV transparent samples. For example, generally speaking, people say saturated hydrocarbons are UV transparent. But in reality, now you know, they are also absorbing, but only thing we are not able to see, we are not able to monitor those transitions because they are actually happening below the range of our equipment. Okay. Now, what is a chromophore? So if a sample has to absorb UV region, UV energy, it has to contain a chromophore. And what's a chromophore? Chromophore, molecules having unsaturated bonds, molecules having free non-bonding electrons that can absorb radiation of relatively low energy are called chromophores. Why we are specifying low energy? Because our absorption should be between 190 to 360 upwards, lower energy side. If it is going below 190, you are going to the high energy side. We will not be able to see those transitions. You will not be able to see the absorbance. You will not be able to measure the absorbance of those compounds. And that is why we are specifically mentioning relatively low energy. Anything between which is happening from 190 upwards. Okay, so molecules having unsaturated bonds or free non-bonding electrons that can absorb radiation of relatively low energy are called chromophores. So consider it as it is something like a functional group. Examples include alkenes that contain double bonds, unsaturation, alkenes, alkynes, ketones, aldehydes, phenyl compounds, and so many. These are some of the examples. A chromophore refers to a functional group that absorbs light, such as C double bond C, C double bond O, N double bond N, N double bond O, like that. Okay. Now these chromophores, so at least the requirement is the sample has to contain at least one chromophore. There is a possibility that your molecule may contain more than one chromophore. It can be 2, it can be 3, it can be 4, like that. Then we call it as a multi-chromophoric system. I will show you one or two examples, just one or two examples of multi-chromophoric system. And what we have to keep in mind is when the number of chromophores is increasing in a molecule, the lambda max value will be shifted to longer and longer and longer wavelength. Okay, I will show you an example also for that. And there is one more term you should understand. Students should understand what is an oxochrome. Now you know what is a chromophore. Chromophore has to be there in a molecule, then only it will be UV absorbing moiety. Now what is oxochrome? By itself, oxochrome will not absorb. It has no absorption capability, but it can influence the absorption of a chromophore. So it is something like, consider it something like a catalyst. It is influencing the absorption of a chromophore. Otherwise, by itself, it will not absorb. So that is what is called a oxochrome, functional group that does not absorb in the UV visible region. But what does it do? It has the effect of shifting the chromophore peaks to longer wavelengths. Suppose if there is a compound and it contains a chromophore and it has got a lambda max value somewhere around, say, for example, 254. I'm just giving a random example, 254. Now, sometimes what happens if a oxochrome is present in the molecule, the lambda max may get shifted from 254 to 300. It is going to longer wavelengths. So it has got an effect of shifting the lambda max value to longer wavelengths. One, there is one more effect. It will also increase the intensity of absorbance. Suppose the same compound which was having 254 nanometer lambda max value has got an absorbance value of 0.6. This is an argument sake. I'm giving a very just a figure, 0.6. Now, because of the presence of an oxochrome, the lambda max is getting shifted from 254 nanometer to 300 nanometer. That means it is going to longer wavelength. And at the same time, the intensity of absorption also may increase from 0.6 to 0.7 or more than 0.7. So that is why it has the effect of shifting chromophore peaks to longer wavelengths as well as increasing their intensities. One or two examples of a oxochrome can be a hydroxyl group, OH group, OR group, NH2 group, thiol group, and even some other halogens also can act as a oxochrome. Multiple chromophores can be present in the sample. There is a possibility. For example, look at the last two rows. There is a diolefin, conjugated diolefin. Sorry, in the compound structure, that double bond is not shown. That's just overlook that. Diolefin, conjugated diolefin, having two double bonds, it has got a lambda max around 217 nanometer. And if you consider a triolefin, it contains three double bonds. Each double bond is a chromophorus. Triolefin, conjugated position, you see, you can see the lambda max is going to 250 nanometers. It is going to longer wavelengths. And what is a simple system for an example for a conjugated system in your lab? Everyone knows benzene solvent is a very simple solvent which are using very, very frequently for various types of applications, various types of experiments. And benzene is a 6-membered closed ring. It's a conjugated system. Wonderful UV absorption capability. And lambda max will be approximately around 254 nanometer. And you can imagine any sample which contains a benzene ring will have a strong absorption in UV region. And you can expect the lambda max somewhere around 254. Not exact, may not be exactly 254, but plus minus some, but it may be in the range of region of 254 nanometer. It's a wonderful chromophoric system. And then the next slide is basically showing the importance of a solvent. You have to be extremely careful while selecting a solvent for preparing a solution. And as I told you before, for UV experiment, you have to prepare a very dilute solution. If your concentration is more, you are going to go to the non-linear range. That is what I will tell you what it is. So normally you have to use a solvent and use a suitable solvent and prepare a dilute solution for measurement in UV. Okay, very, very dilute solution you have to prepare. Now, while selecting the solvent, you have to follow what is the type of solvent you are going to use. And for every solvent, there is a solvent cutoff value. For example, I have shown few solvents here. Acetonitrile, 190 nanometer. Chloroform, 240 nanometer. Pure HPLC grade water, again 190 nanometer. It's a cutoff value. What is meant by solvent cutoff value? For example, take to understand chloroform. Chloroform is a wonderful solvent for different types of samples. Now I got, for example, I got a pharma sample, I got a drug sample. And the drug sample has got a lambda max, for example, 220 nanometers, the lambda max of the sample. And my sample is freely soluble in chloroform. But still, I will not be able to use chloroform as a solvent for this measurement because chloroform has got a cutoff value 240 nanometers. And what is meant by a solvent cutoff? It is something like for example, chloroform below 240 nanometer, that is the cutoff value, chloroform absorbance will increase drastically. That means below, if you are coming below 240, the absorbance of chloroform will increase drastically. And if you are going above 240, the absorbance of chloroform will decrease drastically. So it is something like a cutoff line. Below this value, the absorbance will increase, and above this value, the absorbance will decrease. So if my sample has got a lambda max value around 220, even though it is freely soluble in chloroform, I will not use chloroform because chloroform will also interfere in the analysis. So I have to use a solvent which will not absorb at 220 nanometer. I can think of acetonitrile. 190 nanometer acetonitrile is a solvent which is totally transparent throughout the entire range of UV. Right from 190 nanometer to 360, it is a transparent solvent. I can think of using that, provided my sample is freely soluble in acetonitrile. If the sample is water soluble, I can think of HPLC grade water, again a transparent sample, transparent solvent. So you have to keep in mind what is the solvent cutoff value before you select a solvent, either for using as a solvent for your UV experiment. On this slide is also important for those who are using HPLC, where the detector is a UV detector, variable wavelength UV detector. So you have to keep this in mind, otherwise you will select a wrong solvent and there can be variations in the absorbance values. This is another multi-chromophoric system. It's a water-soluble dye sample. And you can see it has got so many benzene rings, and it is a multi-chromophoric system. And definitely it will have a very high absorbance. And because of the multi-chromophoric system, the lambda max will definitely go to a very, very long wavelength. Vitamin A is another example. It's a conjugated system. Vitamin A is an oil-soluble vitamin, normally analyzed by in pharmaceutical companies. Normally it is analyzed by HPLC with a UV detector because it has got a wonderful UV absorbance capability because of the conjugation of vitamin A. So that is a multi-chromophoric system. Now, another simple example is anthracene. It's a polyaromatic hydrocarbon, anthracene. 3 benzene rings are fused together. It's a multi-chromophoric system. And you can see from the slide, the lambda max is going even beyond 350 nanometer. That means it's going more and more toward the visible region because of the multiple chromophores present in the molecule, and the lambda max is getting shifted to longer and longer wavelengths. Now, this is a slide which students should understand. There are 4 different effects that are possible in UV. For this, explaining this, I am just showing a sample which is scanned between 200 nanometer to around 600 nanometer, means scanned across UV and visible region. And this has got a lambda max somewhere around 400 nanometer, approximately. And it's not very, 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 but approximately 400 nanometers, the lambda max. And it has got an absorbance value somewhere around 0.7. Because UV spectrum is a 2-dimensional graph. What you get on the x-axis is the wave number axis in nanometer. And on the y-axis is nothing but the absorbance value. Normal purpose, we take it as 0 to 1 scale. Whereas we have instruments, it can even go to much more higher scales on the UV, on the y-axis also. But normal experiments, we are keeping 0 to 1. And if you keep 0 to 1 scale on y-axis, and this particular compound, you can consider it as around 0.7 absorbance value. So when this sample is scanned between across UV and visible from 200 nanometer to 600 nanometer, it is showing a lambda max value somewhere around 400 nanometer, and it has got an absorbance value of 0.7. Okay. Now there are 4 different shifts that can take place. One is bethochromic, one is hypsochromic, one is hyperchromic, and one is hypochromic. What is meant by hyperchromic? And you can see the directions of the arrows are totally different. When we consider hyperchromic, there is an upward arrow. And when we consider hypochromic, there's a downward arrow. Okay. This means when suppose I am adding a certain solvent to some sample, or the sample is undergone some reaction, we are adding a substituent on the molecule. And because of the effect, the absorbance value is increasing. That is the meaning of your upward arrow. Absorbance intensity is increasing from 0.7, it is going to say 0.8. But your lambda max is not changing. That is called a hyperchromic effect, hyperchromic. And the reverse can take place when we consider hypochromic. That means now the arrow is downward. Your intensity of absorption will decrease. the substituent that has come on the molecule will reduce the absorbance from 0.7, it has come to 0.6. Again, your lambda max is remaining same. So that is hyperchromic and hyperchromic. So hyperchromic is your increase in intensity and hyperchromic is decrease in intensity without changing the lambda max. These are two types. Then two more. One is a red shift and one is a blue shift. Any shift towards the longer wavelength is called red shift. And any shift towards the lower wavelength is called blue shift. Lower wavelength means higher energy and higher wavelength means lower energy. So lower energy side, if there is a shift, that's called a blue shift, called hypsochromic shift. And any shift towards the longer wavelength, that is low energy side, is called a red shift or basochromic. So the arrows are different here. Now there's two more types of substituents. When I'm adding a substituent on my molecule, the compound is having a lambda max which is shifted to longer wavelength. Now initially it was 400. Now it is shifted to say 500. That is lambda max is gone to longer wavelength. But your absorbance intensity will remain same. Originally it was 0.7, even now it is 0.7. There is no change in the intensity, but the wavelength is, the lambda max is changed from 400 to 500. It has gone to longer wavelength side. That means lower energy side, and that is called a red shift or is called a basochromic shift. And again, the reverse can take place. It can go to lower wavelength side. That means from 400, it can come to 300, lower wavelength. That means higher energy side. That's called a blue shift or it's called a hypsochromic effect. So these four different types of effects can take place sometime in UV. That is the reason why sometimes when you change a solvent, originally I am dissolving my sample in a solvent A and taking a measurement, and I'm getting a certain absorbance value and a certain lambda max value. And if I change the solvent from A to B, sometimes you may find some changes in the lambda max value as well as the absorbance value. Maybe because of these type of changes that are taking place in the molecule in the sample whenever there is a change in the solvent, or when a sample is getting converted to a different sample by a reaction in addition of a substituent, the absorption characteristics of the sample also can change. So these are the effects that we can expect in UV. Now, calibration and BS law, and here I should tell the student that UV analysis is 100% quantitative analysis. It is not a qualitative analysis. We'll see what is the reason for that later. Now, there is a light source and UV light is coming from the lamp. Normally, now everyone knows it is a D2 lamp. We are using a deuterium lamp. D2 lamp is the one that is used in the UV region. The light from the source is coming out. That is the incident light. The intensity is represented as I0 and is passing to the sample solution, which is taken inside a sample cup, which is known as a cuvette sample solution. And depending upon the sample type, depending upon the sample concentration, certain amount of energy will be taken by the sample. And whatever light is coming out of the sample, that is a transmitted light, intensity is shown as I1, and that transmitted light will go to the detector. And the ratio I1 by I0 is called the transmittance value, capital T. And if you multiply this by 100, I1 by I0 multiplied by 100, it will give you percentage transmittance. Now you say many times you will hear, my sample has got 90% transmittance. My sample has got 75% transmittance. It is nothing but I1 by I0 multiplied by 100. Okay. And when you talk about quantitative analysis, and that is the only thing we normally do in UV most of the time, quantitative analysis, and these are all governed by certain laws. That is what we are going to see, that two very important basic laws which is governing the quantitative estimation by UV. And there is a third law which is a combination of these two. Number one is called Lambert's law. What is Lambert's law? Absorbance, that is capital A, that is what you get from the instrument. When you keep the sample inside the UV spectrophotometer, you get a reading on the screen, and that is your absorbance value A, and that is directly proportional to the path length of the absorbing medium. That is what is known as Lambert's law. Path length means if I am keeping a 1 centimeter cell, that is my sample cell, that is called a cuvette. It is a normal thing in normal standard cuvette is 1 centimeter by 1 centimeter square. All the 4 sides are 1 centimeter. So the length of the sample solution through which the light is passing is also 1 centimeter. That's called the path length. So the absorbance is directly proportional to the path length of the solution, sample solution. That is Lambert's law. And what is Beer's law? Absorbance is directly proportional to the concentration of the sample. And now we can combine these two, and that is what is known as Beer-Lambert's law. Every student will know this Beer-Lambert's law. That's a very basic requirement for carrying out a quantitative estimation by a spectroscopic method. It has to obey Beer-Lambert's law. Beer-Lambert's law states that absorbance A is directly proportional to concentration and the path length. Okay, what is this? This is what is the Beer-Lambert's law. A is equal to the relation of absorbance to concentration is given by Beer-Lambert's law. A is equal to epsilon multiplied by L multiplied by C. So A is the absorbance. That is what you will directly read from the equipment. The moment you keep the sample, you will get a reading with your A value. Epsilon is nothing but a constant. It is called the molar absorption coefficient of the sample at a certain wavelength. Very specific constant for a compound. Given compound, it is always a constant. And what is basically molar absorptivity? I think for the students' information, molar absorptivity is nothing but the absorption of a 1 molar solution in a 1 centimeter cell. That is molar absorption coefficient. That's a constant. So consider the constant. L is the path length. And path length is also a constant because you are going to use the same cuvette for your standard preparation as well as your sample preparation. So path length is going to be constant for both. So that is also a constant. And there is only one variable in this equation, that is C. C is the concentration. Concentration of the sample is the only variable. So we can rewrite this equation. If I take out epsilon, and if I take out L, both are constants, we can rewrite this equation as A is directly proportional to concentration. So in reality, we can say Beer-Lambert's law is nothing but absorbance is directly proportional to concentration. That means if you increase the concentration, your absorbance value is going to increase. Okay. What is the effect of concentration? I was specifying you have to use a dilute solution when you prepare a solution for measurement, because deviation from linearity occurs at higher concentration. If you use a high concentration solution, you will deviate from linearity. That means if your concentration of the sample is, this is a general statement, your concentration sample is more than 0.01 molar, you can expect deviation from linearity. And what is linearity? There is something called non-linear range of the equipment. Every detector has got a non-linear range. You can see the graph here, what is shown here, linearity graph. We have prepared different concentration solutions, but you can see 1, 2, 3, 4, 5 points are all lying on a single line. They all can be connected by a single line. So that means there is a linear increase in absorbance value when you increase the concentration. And beyond that, after the last point, 5th point, you see there are 3 more concentrations we have prepared, but there is no increase in absorbance. There is no linear increase in absorbance, even though the concentration is going to be more. And that is what is known as the non-linear range of the detector. Every detector has got a non-linear range or a linear range. I mean, whether it is a UV instrument, whether we talk about GC equipment, any equipment has got a linear dynamic range. It's known as LDR, linear dynamic range of the equipment. So whenever you are making a measurement, you have to see that the values are coming in the falling in the linear range, not in the non-linear range. If it goes to a non-linear range, your quantitation will be totally wrong. So you have to see that, adjust the concentration in such a way that the readings are falling in the linear range of the detector. There is something called stray light. Stray light is basically because of the design of the equipment. It's a hardware part. Stray light can be defined as any unwanted light that is coming and falling on the detector. That's called a stray light. It basically because of the design of the hardware, the manufacturer has to take care of this. And if the stray light is more in the equipment, again your analysis result will be wrong, because that can affect your analysis result. Okay, so stray light is defined as detected light of any wavelength that lies outside the wavelength bandwidth of the selected wavelength. That means, for example, if I am selecting 254 nanometer as the wavelength for my measurement, any light which is having a wavelength outside 254, if 250 nanometer light is also coming into the detector, 260 nanometer light is also coming to the detector, they are all unwanted radiations. They are all unwanted wavelengths. They are called stray light. Whereas I want only 254 nanometer wavelength, but 260 is also coming, 250 is also coming. Because of the design of the hardware system, that means your stray light factor is very high, and that is not desirable. Okay, so now we have equipments where we have got very, very stringent regulation for stray light, and some of the high-end applications, high-end, especially some of the research activities where extremely low stray light is required. We have equipments for that. We are using a double monochromator, but those instruments are also very, very costly. Okay. Now, this is the effect of stray light. If the stray light is going to be more, there will be a lot of deviation from linearity. What you want a linear reading. Your instrument should have a linear range. Means if you are increasing the concentration, your absorbance also should proportionately increase. That is what is called a linear increase. But if you look at this slide, if there is absolutely no stray light, 0% stray light, you get a perfectly linear increase, perfectly linear curve you can get. But as the stray light is increasing slowly, so from 0.01%, 0.1%, 1%, you can see there is a lot of deviation from linearity. And if there is a lot of deviation from linearity, that is going to affect your quantitative estimation results. But today we have equipment, but this is all hardware design. The manufacturers are all giving us equipments having very stringent specification for stray light, and by incorporating a lot of changes in the hardware system. But in the course, the instruments also will become much costly. And some of the important applications, what we see for UV visible and UV visible spectroscopy, why we can, some of the major plus points of UV spectroscopy, you keep any sample, you can get a spectrum. UV spectrum is available. Easy sample concentration, quantitative calculations are very easy, very user-friendly software, and affordable instrumentation. Affordable instrumentation means it is not a very high-cost equipment, and everybody can afford. Even that is why even a normal college laboratory also can afford to have even a small-scale industry also can afford to have a UV, because not a very costly equipment. Even though we have got very, very high-end UV instruments available for high-end research work, costing more than 40-50 lakhs UVs that are also available, but normal applications they are not required. I mean, it's a very affordable and very economic equipment price-wise. So these are some of the plus points of a UV spectrophotometer. At the same time, it has got certain limitations also. What are the limitations? Little structural information, because you get very similar spectra. That's a major drawback. If I am giving you two different samples, A and B, maybe two different chemical samples, two different drug samples, by recording the UV spectrum, you will not be able to differentiate compound A from compound B, because many times both the compounds will give you a very, very similar spectrum. That is not the case when we are going to discuss IR tomorrow. These two compounds, if you record an IR spectrum, the spectra will be totally different, and you'll be able to differentiate one compound from another compound. But that is not possible in the case of UV. That is why it has become a very quantitative estimation technique. Nobody is using UV. Normally, no one uses UV for a qualitative identification technique today in industry. But it is an excellent quantitative analytical technique. Because if you go to any pharmaceutical company, big pharmaceutical company, you will find multiple number of UV spectrophotometers in their lab. A lot of pharmaceutical analysis is being carried out by UV spectrophotometer. We are coming to some of those important applications. Agricultural applications, food industry, UV is widely used. Color is a common parameter, what we measure. Consistency of the food formulation is another important parameter. And these are all should be consistent from batch to batch. I mean, these are all appealing. Your color is an appealing factor. Consistency is an appealing factor to the consumer. So if there is going to be batch to batch variation from the same manufacturer, there can be a lot of problems. The consumer will be at will have a lot of confusion as to whether there is any degradation of the sample, whether there's an adulteration of the sample. So a lot of things are coming into the mind as a layman. So the manufacturer also has to see that these variations never occur. Means there should be consistency from batch to batch in terms of color, in terms of consistency. And in food formulations, there are a lot of small amounts of chemicals that is going as preservatives, antioxidants, anticoagulants, and all these compounds are to be very precisely quantified. And people are using UV for that. So UV has got and then for measurement of color, we have got a separate color measurement software that can be used along with the UV. See that your color remains consistent from batch to batch. So we have got a separate color measurement software also available with UV. It's an optional software. Beverage industry, like soft drinks and liquor manufacturing, beer manufacturing companies, color is an important property. And some of the additives that are added in the formulations that are very important, they're all quantified using UV spectrophotometers. Even leaf analysis, chlorophyll content in plant materials, plant origin. Chlorophyll also can be differentiated depending upon the color. Okay, so again, UV can, but that's an academic application, not an industrial application, but we have got plenty of UV applications in agricultural field and of course food industry also. Biological applications, protein analysis, DNA RNA quantification, kinetics, rate of reaction monitoring, and enzymatic reaction. We have got plenty of applications for UV. See, protein can be quantified, DNA RNA quantification. Even we have got certain separate accessory for that. I will show you that towards that. That will be my last slide. And so a lot of applications in biological field and biotechnological companies, UVs are very routinely used. And industrial applications in pharmaceutical manufacturing. And in pharmaceutical manufacturing, many times, as per the pharmacopoeia requirement, many of the incoming raw materials are analyzed by UV assay, what you normally call as assay in pharmaceutical industry. Find out what is the percentage purity of a drug. It can be, say, for example, I can say my drug is 95% pure, 98% pure, 99% pure. And that determination, many times you can use UV. Many times you do this as pharmacopoeial requirements. And that is one major application, major area of application, pharmaceutical analysis. Then another major area, it's a very really important area for in pharmaceutical industry is the dissolution testing. Once a capsule is made, once a tablet is made, that is to be consumed by the patient for a certain type of disease. And when you take the capsule inside, when you take the tablet inside, how far, because your capsule and tablet all contains not only your API, API means your active pharmaceutical ingredient, along with that a lot of other compounds are there. For example, if you take crocin tablet we normally take for whenever you get a temperature, you take crocin tablet. Active pharmaceutical ingredient is nothing but paracetamol. Paracetamol, if you take a crocin tablet and weigh, it is more than 1 gram or maybe 1.2 or 1.3 gram weight. But in this, normally only 500 milligram of paracetamol is the remaining 600 or 700 milligrams or some other things, which are non-active components, which are called excipients. They have biologically absolutely no action, but they are required in the pharmaceutical manufacturing, tablet manufacturing. Okay, so when you consume this tablet, when it goes inside your stomach, and fast at what time the active drug is available at the site where it is required. And that can be monitored by at what time, at what this thing, the active can be released from the formulation. And that is what we normally study in dissolution testing. And dissolution testing can be carried out for a capsule, can be carried out for a tablet. And once you, then there are a lot of requirements. These are all done as per pharmacopoeial requirements. And you have to prepare a buffer solution having certain temperature. we have to replicate a system that is like our stomach fluid, 37 degrees centigrade, so having certain pH value, and then you drop a tablet or a capsule, and then you start rotation with a paddle. And for the paddle also, the RPM also, there are regulations. What type of paddle you have to use, what type of what RPM you have to give. These are all regulated in pharmacopoeia. And the moment you drop a tablet, that is a zero time. And after that, when you start, the paddle, it starts revolution. And at periodic intervals, you have to take out a sample, small aliquot of the sample, and test how much active ingredient, how much the active drug has come out in the solution from the tablet. That is what we are going to measure. And this is to be periodically checked. And for this, we can use an HPLC system, but HPLC system is time consuming. Yeah, there is a mobile phase preparation, there's a column selection, the column stabilization time, lot of time consumption will be there. Whereas UV is going to be much, much faster. That is why today, if you go to big companies, pharma companies, you will find multiple number of UVs. When I went to a big pharma company in Mumbai, I saw almost 40 dissolution systems. And and for these dissolution systems, they are using multiple UVs, a major application. Similarly, content uniformity, cleaning validation. We have cleaning validation because most of pharmaceutical drugs are manufactured by batch process. One batch is manufactured. After that, the kettle and the reaction vessel, they are all to be cleaned. And because the next day you are going to manufacture a different drug. So nothing from the previous drug should remain inside the reaction kettle or the vessel, so that no contamination will take place. That is what is known as after the cleaning of the kettle and the reaction vessel, there is something called cleaning validation which you have to carry out. And that can be done by UV, that can be done by HPLC, that can be done by TOC analysis. But UV is considered as a very simple technique. So many times people employ UV for that. So a lot of applications in pharmaceutical industry, UV is an absolute must in a pharmaceutical industry. Similarly, in chemical manufacturing also, quality control, raw material testing, intermediate testing, a lot of applications. And so these are all coming under industrial applications. And academic and government applications, environmental testing, contaminants in streams and water sources. There is a slide coming later, so I will explain what is that. And research activities. And a lot of today people are working on solar cells and thin films and solar batteries and all. And not normally, all these are all related to energy. And where in the course of the study, people are actually working on different types of optical materials. And there they are concerned more about the reflection properties and the transmission properties of these materials. And we have got different accessories for all these. So we can offer different types of accessories for different types of research activities. These are all purely academic research. They are not industrial applications, but we have got sufficient number of accessories for doing these type of activities, these type of research activities involving optical materials, and material characterization. And academic students also can use UV for their projects and other things. So it is a very, very simple equipment which has got wide applications in academia and lot of applications in other research laboratories. Coming to some important applications, briefly discussing out. One is I want to start with the protein melting temperature. It's a very important application, especially people who are working in biotechnology and biological field. The absorbance spectra of proteins result largely from the presence of aromatic amino acids. And what are these amino acids present in protein? Tryptophan, tyrosine, and phenylalanine. And these are the aromatic amino acids due to which it has got a absorbance characteristic. A protein at room temperature has got a very specific tertiary structure. That's a protein structure at normal temperature. And that creates a specific electronic environment for the aromatic amino acids. Now, if this protein in solution is heated at a certain temperature, the structure will unfold, or that is what we normally call the protein is melting. And during the course of melting, there will be the structure, the loss of structure will be there. And it will lose the structure. And when it is losing the structure, the electronic environment of the aromatic acids also will change, and which in turn will result in changes in the absorbance values. And that is how we normally do the protein analysis. Okay, similarly, nucleic acid melting temperature, another important application for people who are working in biotechnology. Deoxyribonucleic acid DNA in normal state comprises of 2 strands of deoxyribose molecules. And these 2 strands are helically bound around the same axis. You can consider it as a rod. Consider it as a rod. And there are 2 strings are helically bound together around this common axis. And how these 2 strings are bound? They are bound by hydrogen bonds between purine and pyrimidine bases. Adenine is joined to thymine and guanine is joined to cytosine. So there are 2 bridges. One is an AT bridge and one is a GC bridge in the DNA molecule. And depending upon these 2, the absorbance value also will be changing. And these bases are primarily responsible for the UV absorbance of DNA. And we always do the DNA quantification at a lambda max value of 260 nanometer. The standard method where we carry out the analysis at 260 lambda max value. So what is normally talking about nucleic acid melting temperature? As in any multi-component system, the observed absorbance of a DNA molecule is the sum total of the individual absorbances. Absorbance of DNA is because of absorbance of adenine plus absorbance of guanine plus that of cytosine and that of thymine. However, the observed absorbance is always significantly less than the expected because the hydrogen bonding between the bases will change their electronic environment. When a molecule is heated, the hydrogen bond is going to break and the double helical structure is going to unwind and the absorbance is going to increase. That is why we always heat the system, and then at a certain temperature, the melting is going to take place. That is known as the denaturation process, or it is called as melting of the DNA. So what we normally do, the DNA melt experiment, the temperature of DNA solution is increased in a stepwise fashion. And the absorbance at 260 nanometer at each temperature is measured and plotted as a melting curve. So what we normally do is we plot a melting curve. Lambda max is fixed at 260 nanometer. Gradually increase the temperature. And at each temperature, we are going to measure the absorbance at 260 nanometer. Lambda max is not going to change. And then the midpoint of this curve is known as the TM. It is known as the melting temperature of the DNA molecule. And that gives a lot of information depending upon how many pairs of GC and AT connections are in their molecule. This temperature, this TM value can change. This depending upon the pairs of GC and AT, this temperature can change. That can give a lot of information to the biotechnologist. So DNA melting temperature, the melting peak, we have got a separate accessory for that. We will see that towards the last of this session. And then we can use GC for different types of kinetic enzyme kinetic assays. Direct UV visible analysis of a compound, especially a complex biological sample, is very difficult because of the differences. Separation of a target compound will be time consuming and impractical for routine analysis. Then we can actually resort to enzyme assays. Enzyme assays can be used in the indirect analysis of a compound or a group of compounds in a very difficult matrix sample. Any change in the sample following addition of an enzyme will result only from the reaction of that specific compound. The enzyme will react to a specific compound, the compound-specific enzymes you are adding, and then because of the enzyme activity, the compound's absorbance can vary, and that can be easily measured by a UV spectrophotometer. So we have got a kinetic mode also in the software system, which can be used for these type of analysis. Okay. Now, UV spectroscopy in pharmaceutical analysis, applications in pharmaceutical analysis, a very robust workhorse. UV is a very robust workhorse method for the quantification of drugs in formulations where there is no interference from excipients. Determination of pK values, determination of partition coefficients used to determine release of drugs from formulations. That's what I was telling about capsule and tablets release of active pharmaceutical ingredient from the formulation. Okay, now UV spectrum of a drug also can be found out. But then what are the strengths of UV? An easy to use method, a very cheap method, very simple method, and it's a very robust method offering good precision for making quantitative measurements. That's why we are specifying quantitative analysis, normally not used for qualitative analysis. Okay. And what is the limitation? Only moderately selective. That is the main limitation of UV. It cannot differentiate compounds based on the UV spectra, because most of the time for different compounds it will give you very, very identical spectrum. So differentiating one compound from another compound will become really difficult. At the same time, it can be used for quantification. For example, I'm giving you two different steroids. One is hydrocortisone and one is beta-methasone. And on the left-hand side, you can see the UV spectrum recorded from say 200 nanometer to 300 nanometer. And you will see both the UV spectra are very, very similar. There is a very slight shift in lambda mass, but that is very insignificant. More or less, you can see there is more or less very similar spectrum. So even though the compounds are different, one is hydrocortisone and one is beta-methasone, by recording the spectra of these two compounds, you will not be able to make out which one is hydrocortisone, which one is beta-methasone. So qualitative identification become very difficult based on UV spectra. If we look at the lambda max values of some of the steroids, hydrocortisone, beta-methasone, clobetasol butyrate, beta-methasone sodium phosphate, you look at the lambda mass values, they're all 240, 240, 241. They're all more or less same. So that means you cannot differentiate the compounds from a UV spectrum. For example, say UV spectrum of phenylephrine under acidic conditions and basic conditions. Even though there is a slight change in the intensity, if the lambda max is going to be more or less identical, they're very, very close to each other. It's maybe very difficult to differentiate by recording only the spectrum. So that's a major drawback for UV. And that is the reason why today we are using UV as a quantitative analytical technique. Another important area is assay of penicillins by derivatization. British Pharmacopoeia utilizes the formation of a derivative in order to quantify penicillins in a drug formulation. Because the reason is some of the penicillins do not have a distinctive chromophore. And because there is no chromophore, it cannot directly absorb UV. So what we do, we chemically convert the sample by reaction to a different entity which has got UV absorbance. Now, using a formation of a complex with mercuric ion in presence of imidazole as a catalyst, a derivative of penicillin can be produced, and it has got absorbance somewhere around 325, between 325 and 345 nanometer. We can conveniently measure it. And this assay method is used by British Pharmacopoeia for the analysis of preparations containing ampicillin, amoxicillin, fluoxacillin, and flucloxacillin, etc. And this is what this is the reaction of penicillin with mercury imidazole reagent, and then you get a complex which has got an absorbance somewhere around 325 nanometer. Multi-component analysis. Spectrophotometric assay of a pharmaceutical drug often involves the measurement of absorbance of samples containing one or more absorbing components. Your formulations, as well, we will talk about formulations. You want to quantify a certain drug, but it also contains some other material which may also interfere with the analysis. So it's a multi-component system. It's not a single compound. The pharmaceutical analyst encountered the situation wherein the concentration of one or more components is required in a sample which may contain other absorbing compounds. Normally we call it as excipients that can interfere with the determination. So that's a major problem. So in that case, what we do normally, the basis for multi-component analysis based on the fact that at a given wavelength, the absorbance of a sample solution is the sum total of the absorbance of all the components present in the sample. Assumption number one. Second one is the excipients present in the formulation are not absorbing at the selected wavelength. Here comes the importance of your lambda max selection. And you are going to see a slide for this. So there you will understand the importance of your lambda max selection. And that's very, very critical, especially when you talk about multi-component samples. Derivative spectroscopy, I'm not going into details too much because time will not permit me. I'm just showing you 1 or 2 slides. Derivative spectroscopy is an advanced spectroscopy technique based on the derivative spectrum which are generated from the zero order spectrum. So when you normally keep a sample in a UV spectrophotometer, you get a spectrum, and that is called the zero order spectrum. And from this zero order spectrum, you can prepare derivative, first order, second order, like that. Okay. So the derivatization of your zero order spectrum can lead to separation of overlap bands. That means your sample contains 2 different compounds, and both the compounds are absorbing more or less very close to each other at a certain wavelength. That means the lambda max values are coming very close to each other. So there is something called overlapping. It may not be 100% overlapping, partial overlapping. At the same time, you are not able to quantify them properly because both the lambda max values are coming very close to each other. In that case, if you apply a derivative technique, you can quantify both the compounds very conveniently and comfortably. And that's why the derivative spectroscopy is not used very widely in industry also. If it is required only, then people use derivative spectrum. And otherwise, because higher order derivatives also generates a lot of noise level. That means your signal to noise ratio will come down, sensitivity will drastically reduce. That's another drawback of derivatization. So it is to be used only if it is absolutely essential, otherwise no. Okay, so this derivatization method allows the quantification of 1 or more targets without any initial separation. Now, derivative spectroscopy, lambda A by the rate of change of absorbance with respect to wavelength is plotted against the wavelength. That is what you are going to plot. And the derivative spectrum contains sharper peaks. Well, because when you initial your zero order spectrum, you are having a very broad overlapping peak. When you are converting it to a suitable derivative, you are getting sharper peaks where a better location of peaks and wavelength maxima can be achieved. So that means without a physical separation, you are separating these 2 absorbing moieties so that the lambda max values can be clearly defined, and those values can be used for the separate quantification process. However, please remember, the derivatization order increases, the noise level also will increase. That means your signal to noise ratio will decrease. That means the sensitivity will decrease. So if you are happy with your zero order spectrum, if you can work with the zero order spectrum, never think of a derivative spectrum. These are what you see at the top is called the zero order spectrum. That is what you get from when you keep the sample and you record the spectrum. That's your zero order spectrum. And out of this, you can prepare first order, second order, third order, fourth order. Okay, so these are the 4 different derivative techniques you can prepare. And certain things I am skipping because of my time limitation. And a derivative spectroscopy is an excellent technique for determination of multi-components in a sample if they can be resolved by a suitable derivatization process. Okay, so in this compound, in this slide, I've shown 2 different compounds, X and Y. Originally, if you look at the dotted blue graph, that is an overlapping peak where the lambda max values are coming very close by. They are not properly resolved. By employing a suitable derivatization of first order spectrum, we can, suppose your target is X compound, you can quantify X compound very comfortably, so that no interference from Y will come. So that is why we can X and Y can be separated by derivatization. And then we can quantify both of them independently without any interference. These are some of the examples. Third derivative at 240 nanometer used for the determination of aceclofenac in presence of diclofenac. It's a pharmaceutical application. Second derivative for the determination of acyclovir in presence of guanine. And some examples are shown. These are all pharmaceutical applications. But unless it is required, derivatization technique is not to be used because unnecessary. It will increase the noise level and reduce the signal to noise ratio. That means your sensitivity will reduce. Little bit about the components. These are the basic UV visible spectroscopy basic components, starting with the light source. Then you have monochromator, and then sample compartment, detector, and finally the output, software and your PC. Now, why the light what is coming from the source has to pass through monochromator? What is a monochromator? Monochromator means the light that is coming from the source is a polychromatic light. And what is a polychromatic light? Polychromatic light is a light of all wavelengths, different wavelengths. Whatever is coming from the light source, it will contain multiple number of wavelengths. That is why it's another polychromatic light. Now, this polychromatic light is to be converted to a monochromatic light. Monochromatic light means a light is having a single wavelength. Converting multiple wavelengths into a single wavelength. That means conversion from polychromatic light into monochromatic light. That is what is achieved by a monochromator. And that single wavelength light is passing through the sample compartment, because your sample, you know what is the lambda max. Suppose your sample is having 254 is the lambda max, then only 254 nanometer light should pass through the sample compartment. Whereas the light coming from my source will contain so many wavelengths, right from 190 to 360. Out of which I want only 254 nanometer wavelength light to pass through my sample compartment. So I am using a monochromator to select this. So this monochromator will select this 254 nanometer wavelength from the polychromatic light, and then that will pass through my sample compartment. And then whatever is coming to the sample compartment will go to detector and go to the out. So main parts of a UV visible instrument is the light source, wavelength selector. So monochromator is also known as wavelength selector. Once upon a time we were using filters, but today we don't prefer a filter because it has become outdated. Normally we prefer only monochromators. Monochromator is called a wavelength selector, sample container, that is a sample compartment, detector, and your readout device, your software. Single and double beam instruments, and that difference also I will tell you. So this is a single beam equipment. There is a light source. Whatever the light is coming, it is falling on a wavelength selector, that is a monochromator, passing through your sample and then falling on the detector. This is a single beam spectrophotometer. There is a difference between a single beam and a double beam. That is what you are going to see. And today people prefer a double beam equipment as compared to a single beam equipment. Okay, that we'll see. Okay. Source of light, depending upon, I told you in the beginning, in UV visible spectrophotometer, we have got a UV source, we have got a visible source. And the UV source is normally a deuterium lamp. And that is what is working in the UV region. And it can work from say 190 to 360 nanometer. Here I am shown as up to 400 nanometer, because taking into consideration the overlapping region also. That's why I'm showing the up to 400. The strictly speaking, UV region is from 190 to 360. And you know 360 to 400 is overlapping region where a lamp change takes place. Okay. Now, if you consider a visible region or a near infrared region, you have got a tungsten filament, tungsten halogen lamp. And it has got a much wider wavelength range. It can start from approximately 320 nanometer, and it can even go to 2500 nanometer. It is going to NIR region, deep into NIR region. So these are the two sources what we normally keep in our equipment, D2 source and tungsten halogen source. Okay, so depending upon your area of usage, there will be an automatic changeover from the D2 to tungsten halogen. And this changeover will take place for the software. Okay, wavelength selector. Once upon a time, filters were used, but now filters we don't prefer because they are not very accurate. I mean, they're what you call, they are not very sensitive. And monochromators are what is used today in most of the equipments. And we have got different types of monochromators. We have got very, very powerful monochromators that can be used in a UV visible experiment, UV visible instrument. See, this is a, so what filters I'm just skipping. I'm coming to monochromators. So monochromator, they are used for spectral scanning. They can be used for UV visible region. And there are different types of monochromators available. And what is basically a monochromator? Monochromator is nothing but a glass plate over which a thin layer of aluminum, vacuum coating of aluminum is done. And over the surface, we are actually going to cut grooves. Grooves means small. You can call it as a line. It's not exactly, it's a groove. And what is the number of grooves we are going to draw in 1 millimeter distance? It can be 1,200, it can be 1,600, it can be 1,800, or sometimes more than that. You can imagine in 1 millimeter distance, we are going to draw 1,800 lines, 1,800 grooves. These are all cut by laser light. And then this is going to be mounted on a turntable. It is motorized. And when the light is coming and falling on this diffraction grating, and depending upon what wavelength you have selected for your analysis, this turntable will automatically move because it is motorized. It will automatically move. And at a certain angle, only the wavelength what you have requested will come out, and others will be totally blocked. We can see this, for example, we wanted that 612 nanometer wavelength to come out and fall on a sample. It's a visible measurement. So here you can see the diffraction grating, which is the monochromator. Polychromatic light is coming and falling on the diffraction grating, which contains so many different wavelengths. So depending upon, now you are requested 612 nanometer. So the turntable is going to move, and the diffraction grating is going to turn, and at a certain angle, only 612 nanometer wavelength will come out, and all other wavelengths will be totally blocked. And this is how we select the wavelength, and this is how monochromator is actually working. So that is why it is called a wavelength selector. Whatever wavelength you want, it will select and give you from the polychromatic light. So it is converting a polychromatic light into a monochromatic light. Okay. And different types of monochromators are also available. So we are not going to discuss those hardware things. Okay. Now, what is the bandwidth is very important. Bandwidth means the opening through which the light is coming out. If it is very narrower the bandwidth, better will be the resolution. You can see on the left-hand side, initially opening was 2 nanometer wide. You can see you are getting a very broad peak. We reduced it to 1 nanometer. You are getting a partial separation. See that 0.5 nanometer resolution is improved, and then we are coming to 0.1 nanometer. You see 0.1 nanometer, the resolution is excellent. So that means lower the bandwidth, the better will be the resolution. And for some of the pharmaceutical applications, there are certain regulations and pharmaceutical regulations. What should be your bandwidth, so that your resolution, because they are more worried, more concerned with the resolution what you are going to get. Suppose your sample contains an impurity, and that should be properly resolved from your main absorbing species. In that case, your resolution has to be wonderful. And for getting a better resolution, your bandwidth has to be lower. You can see that right from 2 nanometer, how the resolution is changing when we come to 0.1 nanometer. So you have to use a lower bandwidth for getting a better resolution. Okay. Now, selection of wavelength, I told you, is had to be very, very critical. Selection of wavelength is very important. All your quantitative analysis will be carried out at lambda max value. Different samples will have different lambda max values. If you know the lambda max value from the literature, you can use it directly and then go for quantification, no issue. But if you don't know what is the lambda max, you have to go for a scanning. And my colleague will tell you, he is going to have a small session after this. And you have to scan your sample and find out what is the lambda max and use that lambda max for your quantification. So absorbance measurements are always carried out at fixed wavelength using monochromatic light. When a wavelength is chosen for quantitative analysis, 3 factors should be considered. You have to keep in mind 3 different factors. One is whatever wavelength you are going to select should be the lambda max value. Point number 1 you have to keep in mind. Lambda max only is selected for quantification. And lambda max is what? Wavelength where maximum absorbance occurs. That's the definition of lambda max. And this is point number 1. And what is number 2? And by performing your analysis, now here the importance of lambda max is shown in this slide. We have prepared a sample solution having various concentrations, right from 10 to the power of -2 molar to 10 to the power of -5 molar. And in between, there are a lot of other concentrations also. And we are trying to quantify all the different solutions, right from 10 to the power of -2 molar to 10 to the power of -5 molar solutions. And when we are making the measurement at lambda max values, the absorbance of all the solutions can be conveniently measured. And you look at the slide very carefully. I'm going to change the lambda max value. I am going to change my measurement wavelength from lambda max to a different wavelength, lambda 1. Now, lambda 1 is not lambda max. Lambda max is different. Lambda 1 is a totally different wavelength. So when I'm going to change the wavelength of measurement from lambda max to lambda 1, you can see what happens. The absorbance values are decreasing. And you will, very, very interestingly, you will see the 10 to the power of -5 molar solution, the lowest concentration solution, the absorbance I cannot even measure. Because absorbance got to such a small value that I cannot even measure that. The absorbance of all the solutions have drastically reduced when I change the wavelength of measurement. That's the importance of going for the quantitative measurement at lambda max values. So this is one thing you have to keep in mind. By performing the analysis at such wavelengths, it will be sure that lowest sample concentration can be measured with fair accuracy. So that's the importance of selecting lambda max for your measurements. And second point, when you are selecting a certain wavelength, see that lambda, even if you are going to slightly change your wavelength, your absorbance should not differ drastically. In the look at the slide on the graph, I am showing a certain UV visible spectrum, and two bands are selected, band A and band B. Okay, so it is preferable to choose the wavelength at which the absorbance will not significantly change, even if you are going to change the wavelength slightly. Now, if you look at the lambda band A in the spectrum, and even if I am going to change the wavelength slightly on the left-hand side or right-hand side, my absorbance value is not drastically changing. That means that is an ideal wavelength for my determination. At the same time, look at the band B. Even if there is a slight change in the wavelength, there is a drastic difference in the absorbance value. So that means that wavelength is not a suitable wavelength for the measurement. So this is what you have to understand. So ultimately it comes to your lambda max value. And then third one, especially in multi-component analysis, multi-component system. Suppose your sample has got an active component that is a target along with a maybe a interfering component, maybe an excipient, a pharmaceutical formulation, multi-component system. And ideally speaking, lambda max should be selected. Everyone knows lambda max should be selected. But if I am selecting in this particular case, it's a very special case. Even if I am selecting lambda max, my sample will have a wonderful absorbance, no doubt. But my interfering compound is also going to absorb at that particular wavelength. It is going to interfere with my determination. That means for this particular sample, even my lambda max determination is not suitable. Even though theoretically it should be done, but practically I cannot do that. Then I have to find out a different wavelength for my sample. Okay, I know my absorbance is going to reduce, no matter. I'm going to select a different wavelength. Even though my sample target is going to have a slightly lower absorbance, at this particular new wavelength, my interfering component is not absorbing. So you have to find out a different wavelength where interference component is not having absorbance, only your target is going to absorb. So this is another point you have to keep in mind. Okay. Now detectors, we have different detectors. I will not be spending too much of time. These are all full hardware topics. Different types of detectors are available. And in high-end systems, we are using PMT detectors, that is photo multiplier tubes. And there are a lot of other detectors. We have photodiode array is there, photo silicon diode is there. And so different types of detectors are there. And the detectors are devices that convert radiant energy into electrical signal. Okay, a detector should be sensitive. It should be very sensitive and has a very fast response over a considerable range of wavelengths. These are some of the attributes of a good detector. Okay, we can use a PMT, phototubes emit electrons from a photosensitive negatively charged cathode when struck by visible or UV radiation. And they will be multiplied. They are multiplied by diodes and other things. I mean, I'm not going into those details. Okay, so this is how the design of a photomultiplier tube. Coming to last few slides, different types of samples we can analyze, liquids as well as solids. Gas analysis is not possible in the case of UV, but it's possible by IR. In the case of liquids, can be classified into three different types: transparent liquid, turbid liquid, which is called translucent liquid, or opaque liquid. Opaque liquid means a liquid which has got a very dark color, like dark blue, dark red, dark brown, like that. They're called opaque liquids. With a transparent liquid, you don't require any special attachment. You require only a standalone UV, and you can make the measurements in transmittance mode. Keep the sample in the sample compartment and measure the transmittance. No attachment is required. But if it's a turbid liquid, direct transmission measurement is not possible. You have to use an attachment which is known as an integrating sphere. The integrating sphere is to be purchased, that is to be connected to the UV. Then you can go for transmission measurement or reflection measurement of a turbid liquid. And it's an opaque liquid also. You require an integrating sphere, and you can measure only reflectance measurement. So depending upon the type of liquid samples, either you can do a direct measurement if it is a 100% transparent sample, or you require a attachment that is to be used, an optional attachment that is to be used to UV. And similarly, when it comes to solid, it can be a powder material like a pharmaceutical drug. It can be a coating on a glass. It can be a coating on a mirror or a mirrored surface, anything. But here also, you require a integrating sphere or a specular reflectance attachment for measurements. No, you cannot use a standalone UV for that. And reflectance applications, color analysis is coming under this. Reflectance properties of coatings on glass. Suppose many of say I am using a spectacle. Suppose my spectacle has got a anti-reflectance coating, a polymer coating. And once the coating is done, what is the transmission property of my glass? Or what is the reflectance property of my glass? I can study that, but I require an attachment for that. Similarly, physical properties of characteristics of mirror, and then many times even powder samples can be color measurement we can do. But all these will require a certain attachment, not standalone UV. When we talk about reflectance, there are three different types of reflectance: relative specular reflectance, absolute reflectance, diffuse reflectance. There are three different components, and for all these, we have got different attachments. So depending upon the type of analysis, the type of application, we can offer different types of attachments that can be used along with the main UV instrument. And this is what is known as specular reflectance, where the angle of incidence is exactly equal to angle of reflection. That's called as specular reflectance. And there is another thing called diffuse reflectance, because specular reflectance happens only on a polished surface, an even surface. But if a surface is a powder sample, it's an uneven surface, a structured surface, then diffuse reflectance will take place. That means the light beam will go inside, and while coming out, it will come out in different directions, and that is what is known as diffuse reflectance. And if you need to have diffuse reflectance study in UV, you require an integrating sphere for that. Okay, and this is what is integrating sphere. I'm not going into the hardware system, so this is an optional attachment. And using this integrating sphere, you can study diffuse reflectance of the properties of the different types of powder samples and solid samples. You require a standard for this, which is a barium sulfate, which is considered as 100% white material. And this integrating sphere can be used in two different degrees of angle of incidence, 0 degree and 8 degree. Okay, so this is an attachment for UV. This is another attachment, specular reflectance attachment, for examination of optical materials and multiple layers and lenses and other things for material characterization. And this is a measurement of thin films on glass. I told you coating on my glass. I can use a 5 degree relative specular reflectance attachment for this. I can find out what is the effect of the coating on my glass, whether it is actually warding off the UV radiation coming from my PC, whether I'm getting so after the coating, what characteristics have changed for the glass. So these are basically thin film measurements. So measurement of thin films can be carried out by using a certain attachment. This is a solar battery glass. Measurement with a ISR 1503 is a very advanced integrating sphere, and you are actually finding out the transmission properties of this battery glass at various wavelengths. And these are all purely energy-related applications where you can use a UV along with a suitable attachment. And sometimes we can even do chemical complexation for increasing the absorbance of a compound in presence of a different compound and selectively quantifying that. For example, here we are trying to estimate nickel in presence of iron. But here, if you actually, the actual sample, the nickel has got very, very low absorbance value. By adding a reagent, we can create there is a specific reaction between dimethylglyoxime and nickel is getting converted to a complex, and the complex has got a very high absorbance value compared to iron, and this can be very conveniently measured. So we are making use of these type of reactions for samples which are not, because iron and nickel basically are metals. They have no direct UV absorbance. So we are converting these metals into a UV absorbing entity by addition of certain reagents. I mean, I've got one last slide. I've got only 2 or 3, 4 slides now. Absorbing samples. If your sample is absorbing the UV region, there is no problem. You can directly measure the absorbance of the sample using a UV spectrophotometer. But suppose the sample is non-absorbing. That's why I told you about nickel and iron. They are all non-absorbing samples. Okay, now if I want to make some measurement of certain metallic elements, what instruments I'll think of? I'll think of atomic absorption. I'll think of ICP. I'll think of ICP-MS or even ion chromatography. But quite expensive experiments and quite expensive equipments. But if I can make use of UV, it will be much simpler for me, much economical for me. But at the same time, UV cannot measure directly a metallic element or a non-metallic element. I cannot directly measure chloride. I cannot directly measure phosphate. I cannot directly measure magnesium or iron in my sample, in my water sample. And these are applicable to water analysis. These are very, very important applications in power generating companies. Power generating companies, fertilizer companies, petroleum and petrochemical companies, where people are using huge quantity of water for various applications like cooling tower, boiler house, production, generation of steam, using large quantity of water in the boiler. And the water contains some metallic and non-metallic elements. Over a period of time, there will be a lot of crust formation inside the boiler. And if these are not checked, it can eventually even lead to a very big explosion of the boiler. It's a very major safety hazard. So normally they periodically check the water for metallic and non-metallic contents using a UV visible spectrophotometer. At the same time, as I told you, UV cannot find out directly what is the iron content in water. We add a reagent, metal specific or element specific reagent we add. And when I want to find out what is the content of iron in my water sample, I'll be adding a certain reagent. 110 phenanthrolene reagent I add will have a specific reaction with iron, form a complex, and that can be used for, and which has got a UV absorbance. I can, from the absorbance of this complex, I can back calculate what is the iron content in water. Similarly, cadmium, copper, mercury, sulfates, phosphates, all these can be found out by UV. So you are not going to ion chromatography, you are not going to atomic absorption, you are not going to ICP, you are using a simple UV visible spectrophotometer, but each element has to have a separate a selective reagent. We have got a certain model for that, and that model, when you purchase, you will get all these reagents by default. And there's a program pack also coming in the software where even the built-in calibration curves, everything is there. You have to only mix the sample with the selective reagent, measure the absorbance. The rest of the things will be automatically done by the software. Okay. And the last few slides, UV instrumentation. The students should understand what is the difference between single beam and double beam. Single beam means source, monochromator, whatever is coming from the monochromator will pass to sample compartment. directly go to the detector. You have to measure the sample separately. You have to measure the reference material separately. This is called single beam. When you talk about double beam, source, monochromator, and whatever is coming out of the monochromator is bifurcated into two with the help of a chopper. And one will pass to the reference side, one will pass to the sample side simultaneously. And then whatever is coming from the reference and whatever is coming from the sulfur, either they can pass to two different detectors, or again you can recombine these beams with the help of another chopper and pass to a single detector, and it can go to the processor, your signal processor. So that is a double beam instrument. But today, basically, people prefer a double beam equipment because advantage, single beam system, less expensive, cost-wise it is much cheaper, high energy throughput. But what are the major disadvantage? Very unstable beam. Very unstable, so no reference correction, and you are not very sure about your analytical results. That is why single beam equipments are not preferred today. But today, every user wants a double beam equipment. Advantages are more sensitive, more stable beam, and there is correction in case of any fluctuations. There will be an automatic correction because we are using a reference simultaneously. And disadvantage will be slightly more expensive and more electronic parts are involved in this. So that's a major limitation. But at the same, today, when you go to industry, you'll see every instrument that is used in industry is a double beam equipment, because you are very 100% sure of the result what you are going to get. And the basic components, D2 for UV, tungsten filament lamp for visible, Zerny-Turner monochromator. It's a very popular monochromator which we are using in our system. Zerny-Turner monochromator. I told you there are different types of monochromators. Zerny-Turner monochromator is considered a high-end system, high-end monochromator. And there are different types of detectors. The PMT is there, which is a UV. InGas is there, indium, gallium, arsenide, which is to be used in the NIR region. And then we have got photosilicon diode, PDA detector. The different detectors available for GC. It all depends upon what is your application and what type of analysis you want to carry out. Accordingly, you have to select the detector and the system. And last slide is very important accessories. Long path length rectangular cell, constant temperature cell holder, TCC 100 thermoelectrical temperature control cell holder. ISR is normally nothing but integrating sphere. Different types of integrating spheres are available. TMS PC is a attachment for, I told you about DNA analysis, and we have got a very specific attachment called TMS PC for the quantification of RNA, DNA, and it comes along with a special software which is known as TM software, melting temperature software. Because we know TM, the determination of TM, melting temperature, is a very, very critical parameter for the information about the DNA structure. So we have got separate software for that. We have got a separate accessory called CMS PC that's purely used for DNA RNA analysis. And only this long path length cell means, suppose if the sample has got very low absorbance value, you have got a very precious sample, very costly sample, and the customer says, I cannot offer more than such a very small quantity of sample. That's all what is available. Then when the sample concentration is less, sample quantity is less, your absorbance value is going to be very, very less. That means you will not be able to do a proper quantification. And what is the solution? In that case, you remember the Beer-Lambert's law. If I am going to increase the path length, your absorbance is directly proportional to path length, that is Lambert's law. So that means I can use, instead of a 1 centimeter by 1 centimeter standard cell, I can go for long path length cells. Right from 1 centimeter up to 10 centimeter long path length cells are available. So if a sample has got a very, very low concentration, you can go for a long path length sample cell, so that your absorbance value will increase and you can do a wonderful quantitative analysis. Similarly, sometimes constant temperature cell holders are available, they are required, especially when you are doing some biotechnological applications, protein analysis, DNA RNA quantification. Temperature is a very, very important factor. Temperature you have to keep constant. So we have various methods of keeping the temperature constant for a cell. There are constant temperature cell holder is by circulating the hot water,
Okay, thank you very much, sir. That was indeed very informative, in detailed session on UV visible spectroscopy. Now I request Naraju, sir.
Yeah.
Sir, any questions are there in the Q&A?
Or I think,
Yes, ma'am.
Dr. Lakshmi, we can actually have this after Amol completes this session. That's a very small.
Okay.
Okay. So I will stop sharing.
Yes.
And I request Amol to take over.
Yes. Sir,
Yes.
meanwhile, can you access Q&A session?
Yes. And after this, we can have. Yeah, of course, we can have.
Yes.
After Amol completes, we can have a Q&A.
No,
Yeah,
okay. Can you see the Q&A session?
I cannot see that.
Okay.
After that, Amol complete his session.
Yes.
And if someone can read, we will.
Yes. Sure. Definitely, sir.
Amol, you can take over. Amol, please.
Yes, sir. Can you see my screen?
Not yet, Amol.
Can you see my screen?
Amol, it has not come.
Yeah.
At least I cannot see.
Yes.
1 minute. Now?
No,
Now you are.
Yeah, we can see, sir, your screen.
Yeah.
Then sorry.
Okay. Thank you. Thank you, sir. Before I want to start my session, just small session is there, because already sir has covered lots of things like principle, instrumentation, and its application. So I will just play one small video similar to UV for more interaction. So 1 minute.
It's a 2-minute video. That's all.
Excellence in science. Shimazu.
Thank you all. Okay. All of you, can you see my screen?
Yes, sir. It's very clear.
Okay. Thank you, sir, for giving the information to all of us. So myself, Amol Ramiste, Spectro Application Chemist and Toshwin Analytical Private Limited. As Girijan sir has explained the basic principle and instrumentation as well as application of UV, in this session I will explain the software part, which useful for to operate UV very easily and effectively. UV has widely used in the various sectors like pharma industry, chemical industry, petroleum industry, in academic or institutional industry. Also in polymer and dye industry, also they are widely used with different applications. The UV spectroscopy majorly used for the quantitation of determination of the compounds that absorb the UV radiation, which based on the Beer-Lambert's law. It will be used for the detection of the impurity which may be present in a sample, or which can detect absence or presence of impurity in your sample. Also is used for the structure elucidation of organic compounds which help the presence of or absence of saturation, unsaturation of double bond or single bond. Majorly used for the quantitative analysis by using the calibration curve. We can find out the unknown concentration of analyte or sample by using the running the increasing order of the standards linear for the calibration curve. The major objective of this session, like introduction of UV models, Shimadzu, which are running models, then UV software. What are the different softwares or tab used for the UV? Some of the UV accessories, basic accessories, which are used for the different application. Any UV application, which is already explained by Girijan sir. These are the basic models in Shimadzu, like UV 1900, UV 3600, UV 2600, which are now running models in Shimadzu, and UV 1900 is newly launched by the Shimadzu, which having a cover the range from the 1900 to 1100 nanometer, having spectral band 1 nanometer, which is the highest in its class. So it has having a touch screen which will be operate in standalone as well as by using the software. These are the some specification of the UV models, like UV 1900. It is a single monochromator having the detector photodiode, silicon photodiode, and range is covered from 1900 to 1100 nanometer, and spectral bandwidth is single nanometer. While the UV 2600 having the monochromator single, but it has inbuilt detector is PMT with the help of integrated sphere ISR. It will be come with the PMT and in-gas detector. That is, in-gas detector is indium, gallium, and arsenide, which will be cover the range of 190 to 1400 nanometer, and it has a spectral band variable spectral bandwidth from zero point 0.1, 0.2, 0.5, 1 to 5 nanometer, which will give the resolution better for better resolution. The spectral bandwidth will be helpful. Another model is there UV 17 2700, which having the double monochromator. The main use of this double monochromator, which can reduce the stray light. If instrument having the low stray light, it's mean that the measurement, it will be measure the better absorbance of this sample. Then last model is 3600, having a double monochromator. It has three detector: PMT, multiplier tube, in-gas detector, and lead selenide detector, which cover the range is 190 to 3300, which cover near higher range also, and it has a spectral bandwidth more than 2 to 8 nanometer. So move forward. For UV 1900 or U600, 3600, Shimadzu launched new software lab solution UVVs, which having a compliance software like 21 CFR Part 11. The title 21 CFR of Code of Federal Regulation that established the United States for the Food and Drug Administration regulation for electronic record and electronic signature. So Shimadzu UV spectrophotometer is used automatically transfer or store the various types of data acquired or result of performing data or processing data with the lab solution UV software. To perform the operation related to high security data management and security signatures. It has various type of user management that we can create the users at different levels, like users, administrator, reviewer, and we can give the rights to specific users levels, like users they can't produce or they can edit the method, reviewer only review the method or data, administrator can check the data, verify the data. If need to changes in method or data, it can be do at the administrator level. So the in lab solution software, there are four tabs are there, which include the spectrum, quantitation, photometric, and time course. In spectrum mode, we can analyze. In spectrum mode, we can get scan of the spectrum range at specific wavelength. In this program, the user can perform the scan specific or complete wavelength range at, at given wavelength. Once the spectrum is recorded, the data processing like peak labeling, peak area, peak height, or derivatization like for first order, second order, third order reaction can be done in spectrum mode. For spectrum mode, we have to prepare one method. So for the for method preparation, we have to, in spectrum mode, we have to go to the lab solution. In lab solution, we have to select the spectrum program tab. Now we have to create one method. In method, we have to select instrument parameter. So like we have to select the range, how much we want to scan that range, and we have to set the bandwidth of specific range, like 1 nanometer, 0.15 nanometer, 1.1 nanometer. Then we have to select the mode of absorber, mode of measurement, like absorbance, transmittance, or you want to reflectance, we can measure on that. After the method parameters save, we have to save the method and put the sample blank solution in the both the cuvette and place into the sample compartment. Then do the baseline. Here one icon is there for the baseline correction. Then after the baseline, we have to replace our blank sample from the sample compartment, not reference site, only sample compartment with replace with the sample, and run the sample and get the spectrum of your sample. Here we can see the spectrum of one of the sample. Then we can get the data of particular wavelength. It will be recorded. Next, in quantitation mode, this program used to find out the unknown concentration of the sample, absorptions of data of standard and sample measure, further the quantitation of plotting calibration curve. This is the best and quick mode of for the quantitation of unknown sample in pharma industry or chemical industry. The method creation, same like we have to select specific wavelength for the quantitation, and after the selection of the specific wavelength, we have to enter the concentration value of specific standard, linearity standard. And then after the method creation, same like a spectrum mode, we have to put blank solution in both compartment, do the auto zero. Here we have to select only one single wavelength, so we have to do only auto zero. Then you have, after the baseline correction or the auto zero, we have to replace blank sample from the sample site with the standard. Run the standard, we can get the calibration graph. Then after second window, here we can run the unknown sample, which get the absorbance or the transmittance of the specific sample. and get the final concentration of the sample by using the calibration curve. In photometric mode, we can use the measurement of the absorbance or the transmittance or the reflectance of multiple sample at the fixed wavelength or variable wavelength. Like we can measure the absorbance or the transmittance up to the 8 wavelength at a single time. In the display, we have set the method parameter. We have to set the, in method parameter, we have to select the specific wavelength, or if you want to select multiple wavelength, we can add more more than one or two. It's applicable for eight wavelength at a one time. For the photometric, select the lab solution software, and in photometric tab, select the desired wavelength. Then do the baseline or the auto zero blank. Then take the reading of the specific sample. Here, some of the example of how it will be show. Like I will run the specific samples, and we get the specific absorbance of the sample in the graphical represent. Fourth part is a time course, which known as a kinetic mode also, which can absorbance is measured using sample that change in absorbance with the change in the time at the specific wavelength. In this software, we have to selecting time course, prepare the method parameter or instrument parameter at specific wavelength, set the recording time. If you want to record the change in absorbance at specific timing, like 1 minute or 1 second or 1 hours, we can set into the our method parameter. Also, we can set the data interval that I want to analyze my sample at specific timing. So we have to set here specific timing for the method parameter. After the method preparation, we can run the blank solution for the baseline correction, and then in sample side, we have to replace with the sample and run the sample. So automatically we can get the specific absorbance or the transmittance or reflectance a specific time interval, and we can find out the enzymatic activity or bioanalytical degradation from the kinetic mode. The fifth option is a report template. We can customize the report. After the data generation, report preparation is a main important task. Shimadzu having the customized report generator tab, which having a customized report template, we can put here the company name, date, time, logo, text. We can customize the report. Then Shimadzu having a color measurement software, which is a additional software we can purchase from the Shimadzu. This is the additional software, so we can measure the different color coordinates or color difference formula, like LAB value, like lightness, or combination of two colors like pink, red, green, yellow, blue. The value we can get. Also, we can get the information of yellowness of the water. Software is a fully equipped with the convenient graphic functionally include chromaticity diagram, which used for the color measurement analysis. It look like we can measure the L value from here and LAB value from here. So for this color measurement value, we have to run this spectrum. First, you have to run the spectrum in spectrum mode. We have to select the method parameter like transmittance. Measurement mode is transmittance or reflectance, not use the absorbance. So range which will be cover around 380 to 780 nanometer. Then after this sample run in spectrum mode tab, we have to fetch that spectrum in color measurement tab, automatically we can get the LAB value. Then we can this is a comparable, we can compare this data with the standard. We have to run this standard as well as sample, so we can get idea about the difference in color of specific sample. As sir has a cover different accessories in UV, so I have just gone through the some basic accessories in UV. The UV major accessories in UV is a cuvette. Cuvette is a major part, but there are different types of cuvettes are we are using with the different application. First is the standard cuvette. Standard cuvette is normally 1 centimeter path length, having the volume 3.5 ml. It's normally it's come with along with instrument, so it is a basic. If customer having, if it is used for the precious sample, the second one is a semi micro cell. It is used for the specific precious sample. Sample is quantity is very low and customer don't want to waste sample, so this cuvette we can use or suggest for the small volume of sample, which can do, save your sample. Okay, it has a different volume capacity like 50 microliter to 1.4 microliter. So this for the specific application we can recommend semi micro cell cuvette. For third one is a rectangular long path cell. If the sample concentration is low and don't have option to increase the concentration, or the customer don't want to dilute, if customer don't have the chance to increase the concentration or absorbance, then we will suggest the long path cell, which will be light, will be travel more distance or more distance in this sample, so automatically light get absorb more sample. Sample get more absorb the light, automatically increase the absorbance of the sample. So we in this case we can recommend the long path cell if sample concentration is very low. The path length is start from the minimum path length is 20 mm to 100 mm or 2 centimeter to 10 centimeter we can suggest. Fourth one is a short path length. If sample having a high concentration or customer unable to dilute their sample or don't want to dilute their sample, so the short path length cuvette we can suggest. It will be travel light can travel very short distance. Automatically absorbance of the sample get reduced and it will be analyzed very easily. These are some sample compartment accessories which is used in UV for specific applications. Zipper is an accessory that can be used to measure the solution in UV spectrophotometer. If in this zipper unit, if customer having multiple sample in one day, like 50 to 100 samples, so they the multiple washing for the cuvette they have to given, so wasting of time is much uh, as compared to analyze the sample. So we have to clean continuously, we have to take out the sample compartment cuvette and wash with the multiple rings with the blank solution or water, then again put the sample and put this sample into sample compartment, get the reading. So it required much more time. With the help of zipper, we don't want to put sample uh, in the in the cuvette. Zipper unit automatically suck the sample from the sample tube or the beaker, automatically get the reading. So no need to take out the cuvette from the sample compartment, wash it, and again fill the sample and take the reading. So it will automatically reduce your time, cleaning time. Then second is a TCC 100. This attachment permits the measurement of sample cell under the constant temperature condition. It has Peltier cooling, which control the temperature for the sample and reference site at the specific temperature from the 6 degree to 60 degree. So for for the biological or enzymatic activity reaction which perform at the specific temperature, so we can suggest this TCC 100 unit, which will compatible for UV to UV 1900, 2600 or 3600 also. This is long path cell holder, which is used for the long path cell cuvettes. Different like 20 to 100 cuvette we can put here and analyze the sample. This film holder used for the transmission measurement for the thin samples such as film and filters. We can suggest this film holder. Multi-cell compound, we can analyze the multiple sample in one go. Here one cuvette for the reference side and 6 cuvettes for the sample side. Automatically we run the sample, do the baseline with the reference. Automatically after some time interval, it can get taking the reading for 6 sample simultaneously, respectively, one by one. Last is the integrated sphere. Since the light cannot be penetrated in opaque sample, if customer has sample which is not in liquid form or which cannot be transferred into the liquid form, so if the sample is solid form or powder form which cannot be analyzed in UV, with the help of ISR, integrated sphere reflectance, we can analyze that sample. So it is a reflected then on surface. If the sample surface is a plane, then angle of incidence is equal to the angle of reflectance. It called as a specular reflectance. If the sample has a rough surface or ununique surface, the incidence light gets scattered in different direction or diffuse. It's called diffuse reflection. So Shimadzu having one accessory, that ISR 2600. It can fit in UV 2600 or 2600 plus to measure the reflectance or the transmittance of the sample. We can analyze the liquid sample like transparent sample, turbid sample, opaque sample in ISR. Also, we can analyze the powder sample or coating, different type coating materials, thin films, mirror surfaces we can analyze with the ISR. In ISR, the inner part, this inner part of this ISR is coated with the barium sulfate. Barium sulfate has highly reflective property. So automatically, if light is enter from the reference side or the sample side, get fall on. If light is enter on the ISR from the sample site or reference site, that fall on the standard white plate which are placed behind the ISR, which are in coated with the barium sulfate powder. Automatically light get reflected and this light get measured in between the middle part where the detector is installed. Like detector is a PMT and in-gas detector. So after ISR is placed into the UV spectrophotometer, the both side standard white plate is placed. From the light get enter from reference side and sample side get into the ISR. We can do the baseline for the ISR. Then from the sample side we have to replace the standard white plate barium sulfate standard white plate with this sample. Automatically we get we get measure the transmittance or the reflectance majorly reflectance of the sample. If you want to measure the transmittance, we have to place our liquid sample before the light enter into the ISR compartment. So automatically light get transmit from the reference and sample and falls on this white plate barium sulfate and get read on the detector. Automatically we get the spectra of this sample. These are some application of the UV that we can measure in generally, like already sir has explained, like from the UV application like hexavalent chromium measurement by using the UV photometer, also glass transmission measurement with the help of ISR, also diffuse reflectance measurement with the different cloth, like different cloth material with the help of ISR, also different vitamins can be measured with the help of UV spectrophotometer. So these are the some basic information about the UV spectrophotometer and its accessories. If any doubt, please ask. Thank you.
Thank you, Anmol sir.
Thank you.
It's a very good explanation. And sir, we have a couple of questions in Q&A. Should I start?
Yeah.
Hi, I missed some of the session from 10 to 11 a.m. and I would love to get the link to recorded program. Yes, indeed, we are going to send YouTube recorded videos to all the participants who are present today to their emails. Very soon I will be getting it. Another question is, good afternoon, sir. Can we use UV to detect the drug in nanosponges formulation?
Sorry, once again, question.
Can we use UV to detect the drug in nanosponges formulation?
No, it is possible. We can use that.
Okay.
Yeah.
So another question from Prabha. The presentation on basics of UV visible was well explained. In most of the cases, the absorbance to be maintained between 0 to 1 is necessary. Even sir has explained, for anthracene has high absorbance, nearly 2. Because most of the researchers feel that absorbance to be maintained within 0 to 1. So they are diluting or increasing the concentration.
Right.
Yeah, so that's the question, sir.
Okay. So basically, normally speaking, most of the applications, we tell the users to maintain the absorbance value between 0.3 to 0.8 by diluting the sample. But there are certain cases where the dilution is not possible, or the user doesn't want to dilute the sample because some of the inherent changes will take place if you go for a dilution. In that case, you have to measure the sample as it is without dilution. Now the technology has changed. A lot of developments have taken place in the case of hardware system. We have spectrophotometers where we can measure the absorbance even up to 0 to 6 level. And we have done this analysis for some of the major pharmaceutical companies in Mumbai, where they don't want to dilute the sample, and we have used a system where we can put normal UV spectrophotometer. We keep a y-axis range from 0 to 1 absorbance, because we are going to get an absorbance value between 0.3 to 0.6, 0.3 to 0.8. But in these type of samples, whether it's a requirement, where the sample cannot be diluted, absorbance is going to be more than 1. We have systems available where we can even measure absorbance up to 8, 0 to 8. We don't have to dilute the sample, and we have done this type of analysis for some of the pharmaceutical companies. Yes, it is possible. Hello.
Yes, sir. Thank you very much. And one more question is from Dr. A. Banu. For metal oxide compounds, which type of solvent can be used?
What type of compounds?
Metal oxide compounds. For metal oxide compounds, which type of solvent should be used?
I think you have to find out what is the solvent in which the sample is soluble. I cannot often tell you what is the solvent. We need to check the solubility of the sample. And then we have to see whether the selected sample is compatible in the UV range of our working range. So first of all, we need to find out the solubility. Then only we can tell.
Another question from Manu Devedi. Can we do sugar analysis by using spectrophotometer?
Sugar analysis. See, normally what happens in the case of sugar, they don't have a chromophore. That's why normally when people go for sugar and carbohydrate analysis by HPLC, they normally don't use a UV spectrophotometer detector because there is no carbohydrates cannot be directly detected by UV. But we can do the analysis after derivatization. If we can derivatise the sample and convert the sample into a complex which absorbs UV, we can use UV, and from the absorbance of the complex, we can find out, we can quantify the sugar content. Yes, it is possible, but not by direct measurement, but by some chemical derivatization is possible.
Okay, another question from Ansuyam. What are the easy key points to make a choice of solvents?
Easy
key points. What
key
are
points.
The key points to make a choice of solvents?
Choice of solvents for what? For preparing solution. Okay, some of the points I can tell. First of all, check the solubility of the sample in the given solvent. Number one. Okay. Second thing, you should never use a corrosive solvent in the system. Even if the solvent is a good one, the sample is soluble, but the solvent is a corrosive one, you should not use it. So third point, what is the solvent cutoff value of the solvent? That is very, very important. So what is the measurement lambda max for your sample, and what is the solvent cutoff value for the solvent? And that should be appropriate. I gave you an example there. I mean, when I was discussing, suppose your sample has got a absorbance lambda max value around 220, then chloroform is not a suitable solvent because solvent chloroform cutoff value is 240 nanometer. So you have to see the lambda max of your sample and you have to see the solvent cutoff value of the sample. Accordingly, you have to decide.
Okay, sir. Another question from Vijay Anand. To study the optical properties of nanoparticles effectively through UV visible spectrophotometer, is there any standard method available to prepare the solution?
Any standard method? I do not have any standard method for that, but it is possible. But only thing, sometimes we need to develop a method. But there is nothing like a standard. At least to my knowledge, there is nothing like a standard method. But we can do, because we have a lot of accessories. We need to optimize the method. We can do that. But I'm not aware of any existing standard method. I'm not sure, because it may be available. I am not telling no, but at least to my knowledge, I'm not aware.
Okay, so that's it, sir. I have a question for you.
Yeah, please.
Madam, sorry, madam. One more question is missing.
Oh, one more question. Oh, sorry.
So
sir, one more question from Varaprasad.
How can identify overlapping of different groups from peaks?
Oh, sorry. What is the question?
How can identify overlapping for different groups from peaks?
Overlapping peaks. So when you have an overlapping peaks, you have to resort to derivative spectroscopy only. By doing a derivatization, you can actually separate the overlapping peaks and you can quantify two different compounds separately very conveniently. So those type of areas only, normally we recommend a derivatization spectroscopy. Either you go for a first derivative or a second derivative. And these are essentially useful whenever there is an overlapping takes place between two different compounds in the sample, the same sample. So the answer is only to go for a derivatization technique.
Sir, one more question. Which solvent should be used for UV spectrophotometer?
Which solvent?
Which solvents should be used for UV spectrophotometer? Means with are there any restrictions on solvents? These solvents
no. As it is, there is no restriction. As I told you, the solvents, you should know what the solvent cutoff value. You should know what is your measurement wavelength. And the second thing, solvent has to be very, very pure solvent. It should not be a corrosive solvent. And absorbance, whatever absorbance you are going to measure between 190 and 360 nanometer. where is the solvent cutoff value? For example, if you select a solvent like acetonitrile, it's a completely transparent solvent throughout the entire UV region from 90 to 190 to 360 nanometer. But if you go for a solvent like chloroform, any measurement below 240 chloroform is not suitable, but anything above 240 chloroform can be used. Absolutely good quality HPLC grade water. It is a completely transparent solvent from 190 to 360 nanometer. So if your sample is water soluble, you can use water. So there are a lot of solvents available. You should know what is the range where you can use depending upon the cutoff value. And the solvent should be very, very pure, ultra pure, and it should not be corrosive. That's all. And you should not react with your sample. That's all.
Another question, actually, sir has answered this one already. I will just read the question. List the non-aqueous solvents used in UV spectrophotometer. That's what sir has mentioned already.
Yeah.
Acetonitrile, chloroform, etc.
Yeah.
So, sir, now I think no more questions. I would like to ask you one question. So you have mentioned in your presentation regarding UV visible derivative spectroscopy. So it is very, very useful.
Okay.
My question is, can we use this technique with the normal UV visible spectrometer, or it is completely different spectrometer?
No. There is nothing like a special spectrophotometer.
Okay.
It is a normal spectrophotometer, but this is a function of the software.
Function of the software.
So it has nothing to do with the hardware part or a specific what you call model. Nothing like that.
You mean that
it is a part of the software.
You mean that we can measure the normal UV spectra, later we can process it.
Exactly. It's a mathematical processing.
Yes, sir.
It's a part of the software operation.
Yeah, sir, indeed it was very informative and in detail session. Really, we enjoyed. And all the participants, thank you for your participation. And tomorrow, exactly session will start 10 minutes before. Please try to log in by 9:50. And tomorrow's session will be on FTIR spectroscopy. Right, sir?
Today we have taken at least about 15-20 minutes more because we started late. That's the only thing. Tomorrow we'll be able to end the session much before this time.
Yes. Participants, do you have any questions to the speaker? Please raise your hands if anyone wants to talk to sir. And sir has posted some assignment questions.
5 questions. I will be starting with that tomorrow morning before I start with my IR session. And any student can answer. And these are very, very simple questions. If you have listened to what I have spoken now today, I mean, you will be able to, in hardly a few seconds, you'll be able to answer those questions. I hope all the students have noted those questions. So tomorrow when we start at 10 o'clock, I'll be asking for the answers from the participant students.
Yes. So participants, tomorrow please join early, 10 minutes early, and try to get the assignments done. And if you have any questions also regarding today's session, tomorrow sir will answer. Thank you, sir. Thank you for a very informative session. Everybody is saying very informative. And thank you, Amol sir, for your very nice explanation regarding instrumentation.
Thank you. Thank you.
So with this, I will end the session.
Yeah.
And tomorrow,
Thank you.
Tomorrow, see you. Sir.
Tomorrow we will also log in around 9:45. So that sharp 10 o'clock we can start the session.
Yes.
And we can also end the session by 1 o'clock.
Yes.
Okay.
So that's it for now, participants. Thank you for your active participation throughout, and see you tomorrow.
Thank you, all the participants. Thank you. We will meet tomorrow morning.
Yeah, thank you, Girish sir, for you.
Thank you, sir. Thank you.
Thank you.
I will log out, sir. We will log out now.
Yeah. Yes, please you log out, sir. Later we will close the session.